Hey there, fellow knowledge seeker. Ready for a deep dive? Today we're tackling something pretty unique even for us. The worlds of cutting-edge AI and its struggle to conquer advanced mathematics.
That's right. You might have heard about AI writing poems or even composing music. But can it prove theorems? Can it solve problems that stump even seasoned mathematicians?
Yeah, that's a good question. So where does this frontier math come in?
Frontier Math is kind of a benchmark, like a collection of completely original, super tough math problems crafted by, over 60 top mathematicians from all over the world. Think Fields medalists, Olympiad champions, really the best of the best.
Okay, so not your high school algebra then. So what makes frontier math so special?
It's specifically designed, right, to test AI capabilities in ways that previous benchmarks couldn't. It's meant to push those boundaries of what AI can achieve in, like, mathematical reasoning.
It's interesting that AI models are already performing super well on existing math benchmarks, right? Like GSM-8K and math. Why is frontier math such a different beast?
Well, you see, those benchmarks, they're mostly like high school or early undergrad level problems. Frontier math goes way beyond. It's tackling problems from fields like, think about this, algebraic geometry, number theory, even category theory.
Whoa, that's some serious stuff. So how are these AI models doing with frontier math? What are the success rates looking like?
Less than 2%.
Real time.
Yeah. Even the state-of-the-art AI models are solving less than 2% of the frontier math problems. Really highlights the massive gap between current AI and us, humans, in the world of mathematics.
Yeah, that's a pretty humbling statistic. What makes these problems so difficult then? Is it just about like crazy calculations or is there something more to it?
Well, many of these problems, they require hours of work, even for, human experts. It's not just about calculation, right? It's about deep understanding, creativity, and knowing those specialized tricks of the trade that, we mathematicians develop.
Tricks of the trade. I like that. Can you give us a little glimpse into like what kind of problems we're talking about here, a peek into the world of frontier math?
Sure. Let's start with one that's classified as, like, high difficulty. Okay. It explores Artin's primitive root conjecture.
Okay, already sounds complicated.
Yeah. It delves into the density of primes that satisfy a particular condition related to the order of integers modulo a prime. Even for, like, seasoned number theorists, this is a tough one. I mean, to even approach this problem, you need a solid understanding of things like Frobenius elements and Artin symbols.
Frobenius element is wow. And the solution itself.
It involves a complex inclusion-exclusion argument, quasi-multiplicative formulas, and really getting into how primes behave in number fields. It's like a masterclass in number theory.
Okay, yeah, I'm starting to see why AI is having a bit of a struggle here. Let's move on to another example, maybe. What other mind-bending problems did you come across?
There's another one, classified as, like, high-medium difficulty. It tasks you with constructing a degree 19 polynomial. But it has these specific properties related to its irreducible components over the complex numbers.
Irreducible components over the complex numbers. So we're in the realm of algebraic geometry now.
We are. This one pulls in concepts like monodromy, branch loci, the Riemann existence theorem. Solving it involves weaving together insights from, like, group theory and algebraic geometry. It shows how interconnected these different math domains are.
It's fascinating how these problems are forcing us to, like, think outside those traditional boundaries. Let's keep exploring. What other challenges does frontier math throw our way?
Well, there's this other problem, medium difficulty, I think. It involves this sequence of integers defined by a recurrence relation. The goal is to find the smallest prime number that satisfies certain congruence conditions, and it allows the sequence to be extended to a continuous function on the p-adic integers.
P-adic integers. Now we're getting into abstract algebra.
Got it. This one draws upon p-adic analysis, recurrence relations, the Scola-Mahler-Lech theorem.
Whoa, that's a mouthful.
The solution. Well, it involves understanding the convergence properties of p-adic logarithms and analyzing how roots of polynomials behave modulo a prime.
Each problem seems to open up a whole new universe of like math concepts.
What about those, medium, low, and low difficulty problems? Are those any easier on the brain?
Well, low difficulty is, relative when you're talking about frontier math. Right. Even those involve pretty advanced concepts, and you need, creative problem solving to get anywhere.
Got it.
For example, there's a medium-low problem. It dives into the representation theory of the symmetric group. You need a deep understanding of Coxeter groups, characters, irreducible representations. The low difficulty one, that one involves counting the number of non-zero points on an algebraic curve over a finite field. might sound approachable, but you still need to master concepts like the smoothness of curves, genus, the Haswell bound, and you're doing intricate calculations over finite fields.
So even the easier problems are pretty hardcore. It's clear that frontier math is in a league of its own. But the creators of this benchmark, they actually interviewed some big names in math, right? Like Fields medalists, to get their take on the difficulty of all this. What did they think? They were all in agreement. Frontier math, brutally hard.
Makes sense.
Yeah.
And what about AI? What do they have to say about its prospects?
Well, they predicted that it'll be years, even with, big advancements, before AI can consistently solve these problems on its own. But they saw a huge potential for human-AI collaboration, though. They imagine AI being these amazing assistants handling those tedious calculations, verifying proofs. But true insight, like real mathematical intuition, that's still a human domain, they believe.
So it's like having a superpowered calculator that can double-check your work, but it's still the human mathematician calling the shots, making those creative leaps. What else do these experts highlight?
They talked about the limited training data available for these kinds of specialized research problems. Many of these concepts and techniques, they only pop up in a handful of research papers. It's incredibly hard for AI to develop the deep understanding and intuition needed to really solve them.
So it's like trying to learn a new language from a few scattered phrases, right? You're not going to get very far. So what does all of this mean for the future of AI and mathematics? Is this a sign that its mathematical dreams are, doomed?
I wouldn't say doomed. I see frontier math as more of a reality check, It highlights the areas where AI excels, things like automation, computation, and the areas where it struggles. Creative problem solving, deep mathematical understanding.
It's not about replacing mathematicians, right?
Yeah.
It's about, augmenting their ability.
Exactly. Frontier math is pushing the boundaries of what's possible in both AI and mathematics, forcing us to ask some fundamental questions about the nature of mathematical reasoning and those limits of artificial intelligence.
This has definitely been a mind-expanding deep dive so far. But before we wrap up this first part, I'm curious, where do we go from here? What's next in this quest to conquer frontier math?
Well, frontier math, it's an ongoing project. It's always evolving with new problems, new challenges. The researchers, they're exploring different ways to evaluate things, like increasing the token limit for AI models, allowing them to reason for longer, run more experiments.
So giving AI more space to think.
Yeah, exactly. And they're working with mathematicians to refine those difficulty ratings, making sure the problems are truly pushing those limits.
It's like a back and forth, right, between human ingenuity and artificial intelligence, always pushing each other to new heights.
That's a great way to put it. But let's take a pause here. In the next part, we'll delve a bit deeper into the specifics, like how these problems are created, how they're evaluated, and what insights we're gaining from AI's attempts to solve them.
It sounds good to me. We'll be back soon to continue our exploration of frontier math. Until then, keep those brains buzzing.
Welcome back. Ready to get into some of the nitty-gritty from the research paper.
Okay, let's do it. What really stood out to you about how they designed this benchmark?
One thing that impressed me was their dedication to making sure these problems were truly original. They brought in a team of over 60 mathematicians from, leading institutions all over the world. Each one had to come up with new, unpublished problems. We're talking Fields medalists, top researchers.
Oh, that's a powerhouse team.
Yeah.
It sounded like they were serious about avoiding any data contamination.
Absolutely. They went to great lengths. They kept those problems from circulating online, used secure channels, encouraged everyone to keep things encrypted.
Wow, talk about going the extra mile.
Yeah. And during the evaluation phase, they limited access to the problems, to make sure everything was fair for all those AI models.
So level playing field for everyone. With all those brilliant minds working together, I imagine they covered a pretty impressive range of mathematical fields, rather.
You're absolutely right. Their expertise, collectively, it spanned areas like algebraic geometry, number theory, topology, combinatorics, category theory.
It's like a who's who of math.
Right. It's like they've created this mathematical melting pot, bringing all those different flavors of thought together.
So it wasn't just about testing AI on one specific area of math. They really wanted to see how it performs across the whole spectrum of modern mathematics.
Exactly. And you see that reflected in the breakdown of those, what are they called? Mathematics subject classification codes.
Subject codes.
Right. Those number theory and combinatorics were most prominent, then algebraic geometry and group theory, but it was really broad, making sure no single area was overrepresented.
They really wanted to push AI out of its comfort zone, huh?
Ah,
See how it handles the full diversity and the complexity of modern mathematics.
precisely. Now, let's talk difficulty ratings. How do you even begin to assess the difficulty of problems like these?
Yeah, that's a good question. You can't exactly give them a star rating on Amazon, can you?
Right. It's way more nuanced. Each author, they gave ratings along 3 dimensions: background, creativity, and execution.
Okay, break that down for me.
So background, that ranged from high school level all the way up to research level. It showed like how much math knowledge you'd need. Creativity, that was estimated as the number of hours an expert would need just to figure out the key ideas for solving it. Gives you a sense of like how novel the solution approach might be. And then execution, that's the estimated number of hours to actually compute the answer once you have those key ideas.
So they factored in not just like the raw knowledge needed, but also the time, the effort, the ingenuity even a seasoned mathematician would have to put in.
You got it. And to be even more accurate, they had a peer review process. Other mathematicians checked the ratings, and any differences, they talked it out and made adjustments.
Wow, talk about thorough. Sounds like they really wanted to make sure those difficulty ratings were as accurate and informative as possible.
Absolutely. Okay, now let's get into the evaluation framework. How did they actually test the AI models on these problems?
Yeah, how did that work?
They developed this really cool framework. It lets the models explore and verify potential solutions, through actual code execution. It's designed to like mimic how mathematicians might experiment with ideas.
So it's not just about feeding the problem to the AI and hoping for the best.
Right. It's about giving the AI tools to test out its hypotheses and like refine its approach based on the results. The AI can write Python code within this framework and it gets executed automatically. The results are then fed back to the AI. It's like giving it a, mathematical laboratory to play around in.
I like that. A mathematical laboratory really captures that back and forth, that iterative nature of math research.
It does. And the researchers, they saw some interesting stuff in how different AI models use this opportunity. Some models like O1 Preview and Gemini 1.5 Pro 002, they kind of submitted their answer quickly without much experimentation.
So like they were relying more on their initial intuition, less of a step-by-step approach.
Yeah, that's one way to see it. Other models like Grok 2 Beta, they were much more interactive, running experiments, refining their approach based on the feedback.
Fascinating. Different problem-solving styles even within the AI models.
Right. And you see this reflected in the number of tokens they use, too. Gemini 1.5 Pro 002, they use the fewest tokens per problem, usually, while others use significantly more. That suggests, more complex reasoning was going on.
It's amazing how those little differences can have such a big impact on performance. Okay, so how do the AI models actually perform against these mathematical giants? I'm ready for the results.
Well, the results were humbling, let's just say that. All the models they tested, even the big ones, O1 Preview, GPT-4o, Claude 3.5 Sonnet, Gemini 1.5 Pro, they all had extremely low success rates.
How low are we talking? Give me the numbers.
No model even hit a 2% success rate on the full benchmark, and for those hardest problems, practically zero.
Ouch. That's a far cry from how they perform on those easier math benchmarks.
It is. FrontierMath has really exposed those limits of current AI in a way no other benchmark has. It reminds us that, we're still early on in this journey, especially when it comes to, like, truly advanced mathematical reasoning.
So even the most advanced AI is still, like, light years away from matching the mathematical power of human experts. But I'm guessing there are still valuable lessons to be learned from these, well, failures, right?
Absolutely. FrontierMath isn't just about measuring what AI can do right now. It's about seeing where it does well and where it struggles. It's like pinpointing those strengths and weaknesses in the world of, advanced math.
So it's like a diagnostic tool, helping us to understand how these AI models work, how they approach complex problems.
You got it. The researchers, they found that models did better with problems that involved probability theory and approximations, but they really had trouble with stuff that needed deep algebraic or geometric insights. It's like they're good at crunching numbers, making statistical inferences, but they haven't quite grasped the more abstract side of math.
Like AI is good at stats, but needs to work on its abstract thinking skills.
Exactly. And those insights, they're crucial for guiding research. FrontierMath is more than a benchmark. It's like a roadmap for AI and math.
It's showing us where to focus if we want AI that can truly grasp math, right? Its beauty, its depth, all of that.
Precisely. It's about bridging that gap between AI and human understanding.
This deep dive has been eye-opening. It's incredible to see how far AI has come, but it's also humbling to see how much further it has to go. So what's next for Frontier Math?
Well, one of their main goals is to, inspire more research in AI. They're hoping to see new approaches to AI training and problem solving, approaches that tackle those challenges that Frontier Math highlighted, and they're planning to expand it too, even more challenging problems, pushing those boundaries.
Sounds like they're throwing down the gauntlet for the AI community.
They are. They're challenging us to think differently, come up with new ways to approach AI, ways that can really capture what mathematical reasoning is all about.
This is really incredible. It's inspiring to see Frontier Math pushing those boundaries. In both AI and math, it's forcing us to look at the limits of our understanding and, strive for something more. Before we wrap up this part, though, I'm curious about how Frontier Math compares to other math benchmarks out there. Is it really that much harder?
It's a good question. And the researchers, they actually address that in the paper. They have this comparison chart. It shows the percentage of unsolved problems across different benchmarks. And the results are, let's just say, interesting.
Okay, I'm intrigued. What did they find?
It shows a clear trend. Those existing benchmarks, they're getting close to saturation, like GSM-8K, math, even AIM, which used to be tough. AI is getting pretty good at those, often approaching, near perfect scores.
So AI is mastering those more traditional math challenges.
It seems that way. But then you look at Frontier Math, completely different story. Over 98% of the problems are still unsolved. It's like, AI's climbed some hills and now it's staring up at Mount Everest.
That really drives home how much harder Frontier Math is. And that's because it focuses on research-level math, right? Not just textbook stuff or competition problems.
You got it. It's about expanding math knowledge, not just rehashing what we already know.
It's like they're asking AI to, actually contribute to new math, to think like a mathematician, not just a calculator.
Precisely. And that requires that creativity, that intuition, that deep understanding, stuff that AI hasn't quite shown yet.
Frontier Math isn't just a benchmark then. It's a challenge, right, to the AI community, a call to push those boundaries.
It is. It's like saying, hey, here are the frontiers of math. Come conquer them if you can.
This is incredible. I'm so inspired by how Frontier Math is pushing those boundaries, both in AI and math. It's forcing us to look at those limits and aim for something greater. But let's pause here and continue this exploration in the next part. We'll delve into the bigger implications of all this, what it means for the future, what it tells us about thinking mathematically.
Welcome back. Ready for the final stretch of our Frontier Math deep dive.
I am. We've covered so much ground already. Those mind-boggling math problems, the challenges AI faces, how this whole thing's pushing the boundaries of both math and AI. But now I'm thinking about the big picture. What does all this research mean, beyond just math itself?
That's the question, isn't it? And the researchers behind Frontier Math, they're thinking about that too. Those reasoning skills you need for these problems. Precise logic, abstract thought, creative problem solving, those aren't just for math. They're essential for progress in any field. Physics, economics, engineering, even art and music. It's that deep creative thinking that drives innovation.
So we're not just trying to, solve some abstract math puzzles here. We're talking about advancing AI to a point where it could change science, maybe even human creativity as a whole.
Exactly. Imagine AI helping us understand the laws of physics, design new medicines, create art and music. It could even tackle social and economic problems. If we can get AI to reason at the level Frontier Math demands, the possibilities are huge.
It's pretty mind-blowing when you put it like that. Makes you realize this research is about way more than just math. It's about, unlocking new levels of human potential.
Right. And that's why Frontier Math is so exciting. It's a challenge, a call to push those boundaries. Imagine a future where AI can truly work with human intelligence and creativity.
This has been an incredible journey. I feel like I've learned so much, not just about math, but about AI and its potential. Any final thoughts before we wrap up?
I think Frontier Math reminds us that we're still at the beginning, exploring AI, exploring our own intelligence. True progress, it means getting out of our comfort zones, challenging what we think we know, and embracing the unknown. Who knows what we'll discover along the way?
Well said. This has been a truly amazing deep dive into the world of Frontier Math. Until next time, keep those brains buzzing. Who knows what frontiers we'll explore next? Hey there, fellow math enthusiasts. Ready for a deep dive? Today we're tackling Frontier Math, a new benchmark in AI and advanced mathematics. Imagine hundreds of original problems crafted by a team of over 60 mathematicians, all designed to test if AI can truly grasp complex mathematical ideas.
It's a huge step, you know? We've seen AI master things like image recognition and language processing, but abstract mathematical thinking, that's a whole different ballgame. FrontierMath aims to change that.
It's definitely ambitious. I've read that even the most advanced AI can only solve about 2% of the frontier math problems. It's a stark contrast to those near-perfect scores on simpler math benchmarks.
Exactly. And that's partly because FrontierMath avoids some of the traps we've seen in those other benchmarks.
Okay, what?
Well, for one, many existing benchmarks are becoming saturated. AI models are hitting a ceiling, almost like they've just memorized the answers to a practice test.
Right, not true understanding. And then there's data contamination, where AI might cheat by recognizing similar problems from their training data.
Precisely. So FrontierMath uses completely original, never-before-seen problems to avoid that.
So AI has to think on its feet, so to speak. What kind of math areas do these frontier math problems cover?
Oh, a huge range. Number theory, algebraic geometry, group theory, combinatorics, even some dipping into category theory and topology.
Wow, that's impressive. But how do we know the AI is actually solving these problems correctly? We can't just take your word for it, right?
Of course not. That's where automated verification comes in. The AI doesn't just give a numerical answer, they submit code that computes it. And then a separate script checks if that code produces the right result.
That's clever. Removes any human bias. But how do we know the problems themselves are well-designed and actually challenging?
That's where the team of 60 mathematicians comes in. Each problem goes through a rigorous review process. Multiple mathematicians check the problem statement, the solution, the verification code, even the difficulty rating.
So it's not just about making hard math problems, it's about making good problems that are solvable but challenging. Sounds comprehensive.
Oh, they've definitely thought it through. To really understand, maybe we should look at some specific examples.
Absolutely. Right on the frontier math problems. Let's see what this AI is up against.
All right, let's start with a high difficulty one, focused on number theory. This one tackles Artin's primitive root conjecture.
Okay, we're diving into the deep end already.
Yeah.
What exactly is Artin's primitive root conjecture for those who need a refresher?
Well, it's a fascinating unsolved problem in number theory. It's about the distribution of primitive roots modulo, a prime number. Basically, it says that for any integer, let's call it a, that's not a perfect square, or megish 1, there are infinitely many primes where a is a primitive root.
So a primitive root is like a generator for the multiplicative group of integers modulo a prime, right?
Exactly. And Artin's conjecture tries to figure out how often a number will be a primitive root as we look at larger and larger primes. Now, the frontier math version doesn't ask AI to prove the whole conjecture, which would be, well, monumental.
Right, that's still unsolved and has stumped mathematicians for ages.
Yeah.
How did they adapt it for frontier math?
They cleverly focused it on calculating a specific density related to the orders of 2 and 3 modulo primes. It involves replacing those error term bounds in the original conjecture with computable finite sums.
So they made this theoretical concept into a concrete problem AI can actually work with. But I bet it still needs some serious algebraic number theory knowledge, right?
Absolutely. The solution involves things like Frobenius elements and Artin symbols. Even a seasoned number theorist would break a sweat on this one.
Wow, okay, so that's one example from the high difficulty category. What else have they got?
Let's switch gears to a high-medium difficulty problem. This one blends algebraic geometry and group theory, asking the AI to build a specific polynomial of degree 19 with unique properties.
Degree 19. That sounds a bit intimidating. What kind of properties are we talking about?
The problem is all about the irreducible components of this polynomial and how they relate. You need to understand monodromy and branch loci, which basically connect the algebra to geometric visualizations.
So we're not just playing with equations anymore. We're thinking about shapes and structures these polynomials represent.
Exactly. And the solution uses some heavy hitters from both group theory and algebraic geometry. Riemann's existence theorem plays a big part here.
Riemann's existence theorem. That's a big one. It connects complex analysis and algebraic geometry, right?
You got it. It shows how beautifully different areas of math can come together to solve a problem. And that's a key part of what makes frontier math so challenging. It forces AI to make connections between fields.
2 problems down, and I'm already feeling my brain working overtime. What other mathematical adventures are waiting in frontier math?
Let's move to number theory and p-adic analysis. This one's medium difficulty and deals with a sequence of integers defined by a pretty intricate recurrence relation.
Recurrence relations, those can be tricky, like a mathematical chain reaction, each term depending on the ones before. What's the challenge here?
The challenge is to find the smallest prime number that fits certain properties related to the continuous extension of this sequence.
Continuous extension. Now we're getting abstract. Isn't that where p-adic numbers come in?
You got it. P-adic analysis lets us extend the usual ideas of distance and limits to number systems that are way different from the real numbers. And here, you need p-adic analysis to see how this integer sequence acts in a different mathematical world.
It's like in calculus, we use limits to see how functions behave as their input approaches certain values. But here, instead of approaching a value on the real number line, we're doing it in the world of p-adic numbers.
That's a great analogy. To solve this, you'll need the Skolem-Mahler-Lick theorem from number theory.
I've heard of that, but could use a quick reminder.
Basically, it says, if we have a sequence defined by a linear recurrence relation, then the spots where that sequence hits 0 is a combination of a finite set and some arithmetic progressions.
So it helps us understand the patterns of zeros in these sequences. And that's useful for solving this frontier math problem.
Absolutely. It connects the recurrence relation to the properties we're looking at in its p-adic extension.
I'm really seeing how these frontier math problems push AI to think deeply about different math areas. They're not just testing formulas, they're testing the ability to connect ideas and apply theorems in creative ways.
You're exactly right. And we're just scratching the surface. Frontier math is packed with fascinating problems. Maybe we should take a step back and talk about the bigger picture for a moment, how these problems were created, the structure of the whole benchmark.
That sounds like a great idea. I'm definitely curious about how they managed to build such a comprehensive and rigorous collection of challenges.
It's amazing they got such a diverse group of mathematicians involved. Over 60 contributors from all over the world, each with their own specialty. Seasoned professors, rising stars, even some folks who aced the International Mathematical Olympiad.
Wow, the best of the best. But just having brilliant minds isn't enough. How did they make sure the problems themselves were good enough for frontier math?
That's where their rigorous four-step process comes in. Each problem had to pass these tests. Originality. Absolutely no textbook problems allowed. It had to be something new, needing fresh insight to solve.
Okay, makes sense. What else?
Automated verifiability. The solution had to be definite, checkable by a computer program, like a numerical answer or a symbolic expression, something you could verify with SIMPy,
So it can be graded automatically. Makes sense. What else?
Guess-proofness. Love that word. They had to make sure you couldn't just stumble on the answer randomly.
Ah, so the problems are designed to make guessing practically impossible. Clever.
Exactly. And lastly, computational tractability. So it's not just about throwing brute computing power at it. The solution has to be something you could find using normal knowledge in the field, runnable on typical hardware within a reasonable time.
So they've covered all the bases: originality, verifiability, difficulty, and practicality.
It's all about leveling the playing field and testing AI's mathematical reasoning, pure and simple.
Speaking of the problems, we've seen a few examples, but what's the bigger picture? What areas of math are in frontier math? Is it focused on one area or spread out?
It's incredibly broad. To keep track, they use the Mathematics Subject Classification, MSC for short. It's like a Dewey Decimal System, but for math.
Okay, so a way to categorize all this math. What are the biggest areas they've got?
The top two are number theory and combinatorics, about 34% of the problems combined. Makes sense. They often have those numerical solutions that are easy to check automatically.
Right. What else?
Then it's algebraic geometry and group theory, about 14% together.
Sounds like a feast for anyone who loves those areas, but it doesn't stop there, right?
Oh, no, there's more. Algebraic topology, linear algebra, special functions, probability, complex analysis, category theory, even some partial differential equations.
Wow, they weren't kidding about covering the whole spectrum of math.
And it's not just about having different fields, it's how they're mixed. Many problems need a blend of approaches, showing how math is interconnected.
So it's not just about knowing formulas, it's about seeing the connections, the bigger picture. That's what real math is about, right?
Exactly. To see it, they even made a network diagram. Each node is a math subject, and the links show how often they appear together in problems.
That's a cool way to visualize it.
Right.
What are some of the strongest connections?
The most common pairing is number theory with combinatorics, showing up in 13% of the problems. Not surprising, those two go together often.
Right.
Then it's combinatorics with group theory and number theory with group theory.
It seems like group theory is the social butterfly of math, connecting everything.
You got it. It shows how powerful group theory is for understanding symmetry and structure in different areas.
It's great how frontier math captures this. pushing AI to be less like a calculator and more like a mathematician who can use different tools and ideas flexibly.
Exactly. And this diversity goes beyond just the fields. FrontierMath uses over 200 different techniques, and there's a lot of variety in how they're combined.
So no single trick to crack these problems. AI needs a whole mathematical toolbox.
You got it. Even the most common techniques, things like generating functions, recurrence relations, special functions, each show up in less than 5% of the problems. That's real methodological diversity.
FrontierMath is setting a new standard for testing AI's mathematical thinking. Not just how hard it is, but how broad and deep. It's not just about knowing a lot of math, it's about knowing how to use it, how to connect the dots, and solve problems with that mix of creativity and cleverness that mathematicians have.
You put it perfectly. FrontierMath isn't just a benchmark, it reflects the beauty and power of math itself.
Okay, we've got the problems, the fields they cover, the techniques, but how do we actually test how well AI can handle this?
Yeah.
Because it can't be as simple as just giving them a problem and seeing if they get the right answer.
You're absolutely right. FrontierMath's evaluation is designed to mimic how real mathematicians work. It's all about experimentation, testing ideas, adapting based on feedback. It's a dynamic process.
So it's not just about the answer, it's about showing mathematical thinking. That's fascinating. Can you walk us through how this experimental evaluation works?
So picture this. The AI gets a FrontierMath problem, but instead of jumping straight to solving it, it can write and run Python code within the evaluation environment.
So they can experiment, run simulations, see the results of their calculations, just like a mathematician would at their desk.
Exactly. The AI can try different things, gather data, and refine its strategy based on the feedback. It's much more dynamic, encouraging exploration.
It's brilliant. It's testing their thinking, not just their memory.
You got it. And to guide them, FrontierMath uses carefully designed prompts. The first prompt introduces the problem, explains the code capabilities, and emphasizes mathematical reasoning.
So it's not just a sink or swim situation, they get some guidance.
Exactly. And if the AI gets stuck or gives wrong code, it gets continuation prompts with feedback and encouragement to explore further.
Sounds like a supportive learning environment, even for AI. And when it thinks it has the answer, how does it submit it? How's that checked?
When the AI thinks it's got the solution, it submits it in a specific format. It includes a comment marker and a script that saves the answer to a file using the Pickle module. This keeps everything automated and consistent so we can compare different AIs fairly.
Makes sense. So we've got the problems, the evaluation framework, the prompts, a standardized submission system. It's all very well thought out. But I'm dying to know, how do the top AI models actually perform against this challenge? Are we close to having AI mathematicians that can rival humans?
Well, let's just say the results were a bit humbling. They tested 6 leading language models on FrontierMath, including big names like GPT-4, Claude, Grok, and Gemini. None of them even reached a 2% success rate on the whole benchmark.
Ouch, that's a far cry from those near-perfect scores we see on the easier stuff.
It is, and it shows the gap between human and AI abilities in advanced math. FrontierMath is designed to expose those limits and push AI research further.
So even the best AI still struggles with the kind of deep math thinking FrontierMath demands. But there must have been some interesting things they observed. Did any of the models show promise or try unique approaches?
There were some fascinating differences in how they tackled the problem. Some, like GPT-4 and Gemini, tended to just jump to a solution, not much experimentation, almost like they were relying on pattern recognition or intuition.
Interesting.
It's like they were trying techniques from other areas, like natural language processing, and applying them to math. But math often needs a more methodical, step-by-step approach.
Right. It's not always about finding the shortcut. Sometimes you need to explore and hit dead ends to find the right path.
Exactly. And that's where others, like Claude and Grok, showed some intriguing behavior. They did more back and forth, running code, looking at the results, even changing their approach based on the feedback.
So they were being more iterative, more like how a human mathematician might work.
Yeah. It gives AI researchers valuable clues on how to train models to think more flexibly about math. It's not just about raw calculation, it's about understanding concepts and strategies.
So AI hasn't conquered FrontierMath yet, but these tests are giving us valuable data and showing us the challenges ahead. What are some of the main takeaways from this research? What does FrontierMath tell us about where AI is and where it's going?
Well, I think it shows that AI has come a long way, but it's still got a long way to go to reach truly advanced mathematical reasoning. The fact that even the most advanced models struggle with these problems highlights that we need new approaches in AI research.
So back to the drawing board.
Kind of, yeah.
Yeah.
But I see it as an exciting challenge. FrontierMath gives us a roadmap for AI in math, showing us exactly where we need to focus our efforts to push the boundaries.
And where are those key areas? What's next?
One big thing is the lack of training data for very specific math problems. FrontierMath uses completely new problems, which is great for avoiding data contamination. But it also means there aren't many similar problems for AI to learn from.
It's like trying to teach someone advanced calculus without showing them basic algebra first. You need that foundation.
Exactly. So one idea is to create synthetic data that captures the essence of these complex math concepts.
So we could create a massive amount of training data without needing human mathematicians to come up with every problem.
Precisely. Another promising direction is to develop AI that can do more open-ended math exploration, going beyond just solving set problems with a single right answer.
So AI could start exploring uncharted math territory, coming up with new conjectures, theorems, even whole new fields of study. That sounds almost sci-fi.
It does, right? But we're already seeing AI that can generate new math ideas and proofs. It's early days, but it has the potential to totally change how we do mathematics.
This deep dive into frontier math has been incredible. We've explored the challenges, the innovations, the potential of this benchmark. It's clear that frontier math is pushing the limits of both AI and math, making us rethink what's possible and inspiring us to reach for a deeper understanding.
You said it perfectly. Frontier math really shows the power of human ingenuity and collaboration. It reminds us that the pursuit of knowledge, whether it's by humans or AI, has no limits.
As we wrap up, I'm left wondering, what would a world where AI can truly grasp frontier math look like? How would it change math and how we solve problems in general? Something to think about.
Absolutely. The future of AI and math is brimming with possibilities. Frontier math is just the beginning.
Welcome back, everybody. Ready for another deep dive? Today we're tackling something pretty mind-blowing. A new benchmark designed to test AI's ability to solve really tough math problems.
And we're not talking about high school algebra here.
Definitely not. This is the kind of math that keeps mathematicians up at night. The kind of stuff that can take hours to solve, even for experts.
Exactly. This benchmark, called FrontierMath, is pushing the limits of what we thought AI could do in math. The paper we're looking at today lays out this new benchmark and explains why it's so important, not just for the future of AI, but maybe even for how we do math itself.
Okay, so AI tackling problems that would take humans hours or even days to solve. Why are we even testing AI on this kind of stuff?
Good question. See, current AI benchmarks for math, they mostly focus on high school or early college level problems.
So the easy stuff.
Basically, yeah. And AI is already getting near perfect scores on those.
Time to give it a real challenge, huh?
Exactly. Plus, there's another issue with those existing benchmarks, something called benchmark contamination. This means that AI models might be trained on similar problems, so they're not really showing us their true reasoning abilities.
So it's like giving someone a test they've already seen the answers to.
Right, exactly. It's not a fair assessment. So Frontier Math addresses this by using brand new problems that have never been published before.
Okay, so these problems are designed to be truly challenging and prevent AI from just cheating its way to the answer.
Exactly. Now, before we get into the nitty-gritty of these problems, can you give us a sense of just how big this benchmark is, how many mathematicians were involved in creating it?
Yeah, I'm curious about that too.
Well, over 60 mathematicians from top universities around the world contributed to Frontier Math.
Wow.
And these weren't just any mathematicians. We're talking experts in all kinds of fields. Algebraic, geometry, number theory, topology, you name it. It was a massive team effort.
Like a math all-star team.
Exactly. And they weren't just pulling problems out of textbooks. These were original, challenging problems created just for this benchmark.
Okay, so these problems are seriously tough.
Oh, yeah. And the paper outlines a super rigorous process for making them. First, each problem had to be completely original and not easily solvable with formulas or standard methods.
So the AI couldn't just plug in numbers and get the right answer?
Right. They wanted to make sure it required genuine mathematical insight, creativity, not just brute force calculations.
Interesting.
Plus, each problem had to have a verifiable solution, meaning it could be checked by code.
So no room for human bias in the grading.
Exactly. They wanted to keep it completely objective.
Okay, I'm hooked. But what kind of problems are we actually talking about here? Can you give us some examples?
Well, some are like competition-style problems, the kind you might see in the International Math Olympiad, but even more complex.
Ah,
Others are pulled straight from cutting-edge research, like the stuff mathematicians are working on right now.
wow. So we're talking about problems that are pushing the very boundaries of human mathematical knowledge.
Yeah, pretty mind-blowing. And it gets even cooler. They didn't just throw these problems at the AI and say, good luck. They actually developed this innovative experiment-enabled framework for the evaluation.
Okay, what's that all about?
So the AI models were actually allowed to write and execute Python code to test their ideas, just like a human mathematician would do.
So they're not just crunching numbers. They're actually engaging in a more dynamic, exploratory process of problem solving.
Exactly. They're experimenting, testing conjectures, refining their approaches based on the results they get. And it's fascinating because the paper notes that different AI models approach this framework in different ways. Some just ran a ton of experiments, while others went for a quick answer.
Interesting. So we're already seeing different problem-solving styles emerging in these AI models.
Yeah. But here's the big question. How did they actually perform on these incredibly tough problems?
Yeah, that's what I want to know. Did they crack the code?
Well, here's the punchline. Even the most advanced AI models we have today really struggled with frontier math. Like, the best ones only managed to solve about 2% of the problems correctly.
2%? Wow. That's a pretty humbling result for AI.
It is. But it's important to remember that this isn't about AI failing. It's about showing us just how big the gap still is between human and machine mathematical reasoning.
So frontier math is giving us a more realistic benchmark of where AI stands right now.
Exactly. It's a reality check for the field.
Did the paper get into the specifics of how AI struggled? Like, were there certain types of problems that tripped them up?
Yeah, and it's pretty insightful. They found that even when an AI model got the right answer, it sometimes seemed like it was just by chance, not because it truly understood the math.
So maybe stumbling onto the right solution without grasping the concepts behind it.
Exactly. And that really highlights a key challenge for AI in math. It's not just about getting the right answer. It's about developing that deep conceptual understanding that human mathematicians have.
Right, like the difference between memorizing a formula and actually understanding why it works.
Exactly. And that's why they went a step further and interviewed some of the top mathematicians in the world, including Fields medalists, to get their take on all this.
Wow, they went straight to the source. What did these experts have to say about frontier math?
Well, they all agreed that these problems are super challenging, even for them.
So it's not just the AI struggling. These are genuinely difficult problems for the human brain, too.
Definitely. And when asked how long it might take for AI to make real progress on frontier math, most of them said it could be years, maybe even decades, before we see AI solving these problems at a human level.
So AI isn't replacing mathematicians anytime soon.
Not quite. But here's the interesting part. Many of them were really optimistic about human-AI collaboration in math. They see AI as a powerful tool that could help mathematicians with all sorts of things, like automating tedious calculations or verifying complex proofs.
So AI becomes like a superpowered research partner, augmenting human capabilities.
Exactly. Of course, they also talked about the ethical side of things, making sure AI is developed responsibly and doesn't create new problems.
Right, because it's not just about the technical possibilities. It's about using AI in a way that benefits everyone.
Absolutely. And I think that's one of the big takeaways here. Frontier math is about more than just testing AI. It's sparking a bigger conversation about the future of math, the nature of intelligence, and how technology is shaping human knowledge.
I love that. So are we ready to get into the specifics of this benchmark? Like, how do they actually find and create these incredibly difficult problems?
Let's do it. They had this whole collection pipeline, reaching out to mathematicians from all different areas of expertise.
Okay, so a very deliberate process.
Very. They had strict requirements for each problem. It had to be original, verifiable, and resistant to simple guessing strategies.
Sounds like they thought of everything.
They really did. And get this, each problem went through a rigorous peer review process where other experts scrutinized it to ensure quality and accuracy.
Like a super thorough quality control for math problems.
Exactly.
So now we've got this collection of carefully crafted, super challenging problems. How do they actually test the AI? Like, how do you evaluate an AI's math skills in a fair and effective way, especially with these super advanced problems?
That's where this experiment-enabled evaluation framework comes in, which is detailed in section 2.2 of the paper. It lets AI models experiment and try different approaches, just like humans do, by writing and running Python code in a controlled environment.
So it's like giving the AI a virtual whiteboard and some coding tools to play around with. They can tinker and experiment, just like a human mathematician.
Exactly. And this approach reflects how math research works in the real world. It's all about trying things out, hating dead ends, coming up with new ideas. This framework lets AI models go through that same process.
That's a really cool way to test AI. It's not just about finding the answer. It's about the whole process of thinking and problem solving. We've already talked about the overall results being pretty dismal with a 2% success rate. But can we dive deeper into how those AI models actually performed? Like, were there any interesting differences in how they approached the problems? Any hints of progress?
Definitely. So they tested 6 leading language models,
Right.
and they saw some interesting things. Some models, like O1 Preview, were quick to submit their answers without much experimentation. Others, like Grok 2 Beta, took a more exploratory approach, running lots of experiments and trying out different ideas.
So some went with their gut, while others were more methodical.
Yeah, exactly. But neither approach was particularly successful. Even the models that did more experimenting struggled to find the right solutions. And what's interesting is that often, even when a model did get the right answer, it wasn't clear if it truly understood the math behind it.
So back to that idea of mimicking versus understanding.
Exactly. AI might be able to mimic certain aspects of human mathematical reasoning, but it's not yet showing the same depth of conceptual understanding that we see in expert mathematicians.
Makes sense.
And that's a big takeaway from FrontierMath. It highlights just how limited current AI systems are when it comes to advanced mathematical thinking.
Okay, so we've seen how they performed. But how does FrontierMath stack up against other benchmarks for evaluating AI's math skills?
Good question. Section 5 of the paper does a great job of comparing FrontierMath to other math AI benchmarks.
So there are other benchmarks out there.
Yeah, quite a few actually, but FrontierMath is unique in a few key ways. First, it focuses on those super difficult problems we talked about, pushing the boundaries of what we consider advanced math reasoning.
So raising the bar significantly.
Exactly. It's not just about solving basic problems, it's about tackling the really tough stuff that even human experts struggle with.
Got it. What else?
Second, FrontierMath uses completely new problems that have never been published before.
To avoid that benchmark contamination problem we talked about.
Right. It ensures that the AI models can't just rely on memorization or tricks to solve the problems.
They have to actually think mathematically.
Exactly. And the third key difference is the automated verification system. The solutions to these problems can be checked by code, which means they can test a wide range of AI models, even those that are closed source.
So it's a much more objective and transparent way to evaluate AI's progress in math.
Exactly. And that makes FrontierMath a really valuable tool for tracking how AI is developing in this area.
Awesome. Okay, so let's get back to those expert interviews. They sound super fascinating.
Yeah, let's dive into section 6, where they talk to those big names in mathematics. Terence Tao, Timothy Gowers, Richard Borchards, and Evan Shen.
Okay, so we know they all agreed that the FrontierMath problems are incredibly challenging, even for them. And we talked about their thoughts on human-AI collaboration. What other interesting things came out of those conversations?
One thing that kept coming up was this idea of AI as a tool for democratizing math knowledge.
Okay, what does that mean?
Well, Terence Tao, for example, talked about how AI could make advanced math techniques more accessible to people who aren't professional mathematicians.
Oh, interesting. So AI could help non-experts use math more effectively in their own work.
Exactly. It could be a game changer for all sorts of fields.
Like what?
Science, engineering, economics, even the arts. Imagine if everyone had access to AI tools that could help them understand and apply complex math concepts.
That's a pretty powerful idea. But did the experts express any worries about this? Like potential downsides?
Yeah, they did. One concern was about bias in AI systems. Like, if they're not developed carefully, they could end up making existing inequalities worse.
That's a really important point. We need to make sure these AI tools are used ethically and benefit everyone.
Absolutely. Another concern was the potential for AI to stifle human creativity. Like, if we rely too heavily on AI to do all the hard work in math, we might lose sight of the beauty and elegance of human mathematical thought.
Right, because AI should be a tool to help humans, not replace them.
Exactly. We need to find the right balance.
Well said.
So the paper wraps up by talking about the limitations of FrontierMath and some potential directions for future research.
Okay, so they're acknowledging that this is just the beginning of a much bigger journey.
Exactly. And they're very open about the fact that frontier math has its limitations. Like we've already talked about how focusing on problems with verifiable numerical answers doesn't fully capture what math research is all about.
Right, because there's so much more to math than just getting the right answer.
Exactly. They also talk about how the current limitations of AI models make it hard to use frontier math to compare different models effectively.
Like trying to measure something with a ruler that's too big.
Exactly. But they still see frontier math as a really important step forward. It's a starting point, a catalyst for new research, and a way to inspire the development of better AI systems for math.
So a call to action for the AI research community.
Exactly.
Okay, so what are some of those future directions they talked about?
Well, one key area is expanding the benchmark with even more diverse and challenging problems, including ones that involve open-ended tasks like coming up with conjectures and developing proofs.
Wow, so taking AI to a whole new level of mathematical thinking.
Exactly. And they also talked about creating new ways to evaluate AI that go beyond just checking for the right answer. They want to assess things like depth of understanding, originality, and elegance.
So really getting into the qualitative aspects of mathematical thinking.
Exactly. And of course, they stress the importance of continued collaboration between AI researchers and mathematicians.
Right, because you need the expertise of both sides to really push this field forward.
Absolutely. They're committed to keeping frontier math as a public resource, constantly testing new AI models, and providing transparent assessments of AI's progress in math.
That's awesome.
Yeah.
It sounds like they're really building a foundation for the future of AI in mathematics.
I agree.
Well, this has been an incredible deep dive. It really makes you appreciate the power of math and how AI is starting to play a role in this field.
I couldn't agree more. It's been a pleasure exploring this with you.
Now, I'm really curious about those sample problems included in the paper. Are you ready to tackle some mind-bending math?
Absolutely. Let's get into those sample problems and see what kind of challenges AI is facing in the world of advanced mathematics.
Perfect. So the paper gives us 5 sample problems, each representing a different level of difficulty. They range from super challenging problems that would take even expert mathematicians a lot of time to solve to more accessible problems that still require a good understanding of advanced math concepts.
Right. And remember that table we talked about earlier? It does a great job of summarizing the key characteristics of each problem.
Okay, let's revisit that table and then dive into the specifics of each problem. I'm ready to see what kind of mathematical beasts we're dealing with.
Let's do it. Okay, so this table gives us a bunch of different ways to see just how hard these sample problems are.
Yeah, and it's not just about like the level of math, right? It's also about how much creativity you need and how long it takes to actually solve it.
Exactly. So let's look at those column headings again. The first one is problem. Pretty straightforward, just the problem number. Next is author, so we know who came up with each brain teaser.
Okay, then we have background, which gives us that difficulty rating from 1 to 5, right?
Right, 1 being high school level, 5 being research level max.
So that tells us how much expertise you need just to understand what the problem is even asking.
Exactly. Then we've got creativity and execution, which are measured in estimated hours for an expert mathematician.
So how much original thinking and step-by-step work is needed?
Exactly. Then MSc, which is that math subject classification system, kind of like a Dewey Decimal for math.
Right, so it tells us which areas of math each problem falls under.
And finally, key techniques gives us a hint of the tools we might need to solve these things.
Okay, so it's a really comprehensive way to categorize these problems. Let's dive in. Starting with the hardest one, sample problem 1, which has a background rating of research. What makes this one so tough?
Well, this one's from Olli, Järviniemi, and it basically asks us to figure out how often a certain type of prime number occurs. We're dealing with Artin's primitive root conjecture here.
Okay, so already we're in deep water. This isn't textbook stuff anymore.
Definitely not. This is a famous unsolved problem in number theory. And this particular problem, you need to understand things like the Chebotarev density theorem and Galois theory.
Not exactly everyday topics.
Nope. So imagine you've got a prime number, like 7, and you're doing operations with numbers less than 7, but you always reduce the result modulo 7, meaning you find the remainder after dividing by 7.
Okay, modular arithmetic. So 15 becomes 1 because 15 divided by 7 leaves a remainder of 1.
Exactly. Now, the order of a number modulo a prime, say the order of 2 modulo 7, is the smallest power you need to raise 2 to get 1 modulo 7.
So what power of 2 gives us a remainder of 1 when divided by 7?
Exactly. And a primitive root modulo a prime is a number whose order is the prime minus 1. So for 7, a primitive root would have order 6.
I'm following so far, but what does this have to do with Artin's conjecture?
Well, Artin's conjecture says that for any number, there are infinitely many primes where that number is a primitive root. But nobody's been able to prove it yet.
So we're not trying to prove it here, right?
Not quite. This problem is related, but more specific. It asks us to calculate how often the order of 2 modulo a prime is bigger than the order of 3 modulo that same prime.
Okay, so we're looking at how often this specific thing happens as we look at larger and larger prime numbers. Why is that so difficult?
Because proving stuff about how prime numbers are distributed is really hard. It often involves really deep math, like complex analysis. This problem specifically relies on the Chebotarev density theorem, which tells us about how prime ideals split in number fields.
Okay, definitely getting into some complex territory there. I can see why this is considered a research-level problem.
Yeah, it is. The solution in the paper is pages and pages long with all sorts of complicated arguments.
Wow, that's intense. Maybe we'll leave the actual solving to the experts for now. But it's fascinating to see what's out there on the edge of math.
Absolutely. And it really highlights the brilliance of human mathematicians who can even come up with these kinds of problems and tools to solve them.
Okay, let's move on to sample problem 2, which is rated as high-medium difficulty. What's this one all about?
So this one comes from Alexander Kite, and it's a mix of algebraic geometry, group theory, and number theory. You need to build a specific polynomial with certain properties and then figure out its value at a certain point.
Polynomials, that sounds a little more familiar.
Yeah, but the challenge here is understanding how the polynomial is connected to a geometric object, which is a curve in two-dimensional space. You need to use concepts like monodromy, branch loci, and the Riemann existence theorem.
Okay, now you're bringing back some memories from abstract algebra.
Right, so think about a polynomial equation like y equals like 2, 2. This equation defines a curve on a graph. Now, monodromy basically describes how the solutions to this equation change as we move around a loop in the complex plane.
So we're looking at how the curve changes shape as we explore different areas of the complex plane.
Exactly. And the branch loci are the points where the curve, does something special like branching off. The Riemann existence theorem is what connects the algebra of the polynomial to the geometry of the curve.
Okay, so we're using algebra to describe the shape of geometric objects. Sounds pretty trippy.
It is, and the solution in the paper is really clever. It uses group theory and geometric reasoning to actually construct the polynomial. It shows how different areas of math can work together.
That's so cool. Math is like this interconnected web, not just separate subjects.
Oh, right.
Okay, sample problem 3. This one is medium difficulty. What's the deal here?
This one is by Diego Chicharo, and it's all about p-adic analysis and recurrence relations. They give us a recurrence relation, and we have to find the smallest prime number that fits a specific condition.
Prime numbers again, but with a twist this time. Can you explain p-adic analysis and recurrence relations?
Sure. So p-adic numbers, it's like a different way to think about numbers. Instead of the usual decimal system, we focus on how divisible a number is by a specific prime number p.
So we're zooming in on the number line with a focus on divisibility by a prime.
Exactly. And recurrence relations define sequences where each number is determined by the ones before it, like the Fibonacci sequence.
Oh yeah, where each number is the sum of the previous two.
Right. So in this problem, we're basically looking at a recurrence relation through this p-adic lens.
Okay, I think I get the general idea, but the specifics are still a bit fuzzy.
The solution involves a bunch of algebraic manipulations, some p-adic analysis, and something called the Skolem-Mahler-Lech theorem. It's a good example of how we use abstract math to solve problems about sequences and prime numbers.
It's like math is not about memorizing formulas. It's about these powerful concepts and using them creatively.
Exactly.
Okay, let's move on to sample problem 4, the medium-low difficulty problem. What area of math is this one?
This one, from Shreepranav, Varma, and Igandla, is all about group theory. You have to analyze these sets of 4 tuples of matrices and figure out how many different orbits they form under a specific group action.
Group theory. Now we're getting abstract. Can you remind me what group theory is all about?
It's the study of symmetry and structure. It's about finding patterns and relationships when you combine objects in a specific way. A group is a set with an operation that follows certain rules.
So it's about finding order And patterns in how things interact. What do groups have to do with matrices?
Well, matrices can be elements of a group, and group actions describe how a group can change a set of objects.
So in this problem, we're seeing how a group of matrices acts on a set of 4 tuples of matrices.
Exactly. The challenge is to realize that the problem is describing a specific type of group called a Coxeter group.
Okay.
And by understanding how these groups work, we can figure out the answer to the problem. It's a cool example of how group theory can be used to solve problems about matrices.
Math is full of surprises.
No, right?
Okay, last one. Sample problem 5, the low difficulty problem. What's this one about?
This one comes from Alex Gunning. It's about counting how many solutions a certain equation has over a finite field. It's considered the easiest of these sample problems, but you still need to know some algebraic geometry and stuff about finite fields.
Okay, back to equations. Why is this one easier than the others?
The equation is simpler, and we're working with a finite field, so there are only a limited number of possible solutions. But you still need to understand the geometric object defined by the equation, and use tools like the Hass-Weil bound.
So even the easy problem is still pretty challenging.
Oh yeah, it definitely requires some advanced math knowledge,
Yeah.
but these concepts are usually covered in undergrad math courses.
Okay, that makes sense. So even the most accessible problem in frontier math is still a big hurdle for AI right now.
Definitely. It shows how complex math really is and how far AI still has to go to catch up to human mathematicians.
Well, these sample problems have been a real eye-opener.
Right. It gives you a good feel for what frontier math is all about.
Definitely. Now, I'm really curious to hear more about those expert interviews and their thoughts on frontier math and the future of AI in math. So let's circle back to those expert interviews. Hearing from actual mathematicians really adds a whole other dimension to this whole AI and math thing.
I know, right? It's so fascinating to get their perspective. These are like the rock stars of math. The paper talked to Terence Tao, Timothy Gowers, Richard Borchards, and Evan Chen.
Yeah, we touched on some of their insights earlier, like the difference between competition math and research math, and their thoughts on AI collaborating with mathematicians. Did anything else stand out to you from those conversations?
Well, one thing that struck me was how they talked about AI potentially making math more accessible. Like Terence Tao mentioned how AI could help people who aren't professional mathematicians use sophisticated math techniques.
Oh, interesting. So it's not just about helping experts solve harder problems. It's also about empowering everyday people to use math more effectively.
Exactly. It could have huge implications for so many fields.
Like what? Give me some examples.
Well, think about science, engineering, economics, even art. What if anyone could use AI tools to understand and apply complex math?
That's a pretty amazing thought, democratizing math knowledge.
Right. But they also brought up some valid concerns, like if we're not careful, these AI systems could be biased and actually make existing inequalities worse.
Yeah, that's a big one. We need to be super careful about the ethical implications here.
Absolutely. And some of them worried about AI stifling human creativity. You know, if we rely too much on AI to do the hard math thinking, we might lose sight of the beauty and elegance of human thought.
Right. AI should be a tool to help us, not replace us. It's about finding that balance.
Definitely. So in the last part of the paper, they talk about the limitations of frontier math and where this research could go next.
Okay, so they're acknowledging that this benchmark is just a starting point.
Exactly. They're very upfront about the fact that it's not perfect. Like we said before, focusing only on problems with verifiable numerical answers doesn't really capture everything about math research.
Right, because math is about so much more than just getting the right answer.
Exactly. And they also talk about how hard it is to compare different AI models using frontier math, since they all perform so poorly right now.
Like, it's hard to see which model is better when they're all failing.
Yeah, it's like they need a different kind of measuring stick. But even with those limitations, they see frontier math as a huge step forward.
It's paving the way for future research.
Exactly. And they have some exciting ideas for where to go next. One big one is expanding the benchmark to include even more diverse and challenging problems, like problems that involve open-ended tasks, things like coming up with new conjectures and developing proofs.
Wow, so testing AI's ability to actually think like a mathematician, not just solve problems.
Exactly. And they also want to create new ways to evaluate AI, not just checking if it got the right answer, but looking at things like depth of understanding, originality, even elegance.
So judging the AI's work like you would judge a human mathematician's work.
Exactly. And of course, they emphasize the importance of collaboration between AI researchers and mathematicians.
Right, because you need both sides to really make progress in this area.
Absolutely. And they're committed to making sure FrontierMath stays relevant and challenging, and that they keep testing the latest AI models.
That's awesome. It sounds like they're really building a solid foundation for the future of AI and math.
I think so too. It's exciting to see what they come up with next.
This has been such a fascinating deep dive. I feel like I have a much better understanding of what AI can and can't do in math right now and what the future might hold.
Me too. And I think it really highlights the power and beauty of math itself.
Absolutely. To our listeners, we hope this deep dive has sparked your curiosity about AI and mathematics. It's a field that's constantly evolving, and who knows what amazing discoveries are just around the corner. Thanks for joining us on this deep dive. Welcome to the deep dive, everyone. Today we're going deep into some really fascinating stuff.
Oh, yeah.
FrontierMath. It's a benchmark designed to test the absolute limits of AI.
Limits of AI in math.
In some really hard math.
Yeah, and what's so interesting about this benchmark is it's not just, your run-of-the-mill math problems.
Okay.
It's stuff that could stump the seasoned mathematician for hours, days, even longer.
It's true. So, it's really testing the ability to think like a mathematician.
Exactly.
Not just compute, not just crunch your numbers.
Right.
Our source today is the research paper that lays out FrontierMath.
Okay.
And the big question is, can AI actually think like a mathematician?
And that question, that really gets to the heart of, how do you even design a test for AI? That can even compare to the creativity and the rigorous logic that humans bring to math.
Absolutely. So let's dig into this paper and see how they actually did that.
Yeah.
So they start off by saying why we need a new math benchmark in the first place, right?
Right.
Why is this even necessary?
Yeah.
Well, they argue that existing benchmarks are becoming saturated.
Mm-hmm.
The AI models are already getting near perfect scores on a lot of them.
Okay.
So that means they're not really pushing the boundaries of AI anymore.
Right. And there's also this other issue of, data contamination, which they talk about, where some of these AI models might have actually been trained on problems that are similar to the ones in these existing benchmarks. So it's like, knowing the test questions beforehand, it's not a fair...
Not really fair.
Yeah, comparison.
So FrontierMath aims to address both of these issues. Difficulty and data contamination.
Okay.
And how they do that is they've designed it to be way harder than existing benchmarks, and they're using entirely new problems that have never been seen before.
That's great.
To make sure that it's, a level playing field.
Makes sense. That leads to another interesting question, though.
Yeah.
How do you even go about creating these problems for FrontierMath? It's not like you can just take them from a textbook.
Right. So they actually brought together over 60 mathematicians from top universities and research institutions all over the world.
Oh, wow.
To create these problems.
So like a dream team of math wizards.
Yeah, pretty much. And a lot of these mathematicians actually have backgrounds in things like the International Mathematical Olympiad.
Wow. So they're like the elite of the elite.
Yeah. And they set some pretty strict criteria for the problems.
Okay.
They had to be original, meaning they couldn't just be, rehashed textbook problems.
Right.
They had to be automatically verifiable, meaning that a computer could check the answers.
Okay.
They had to be guess-proof, meaning you couldn't just, stumble on the right answer by chance.
Right.
And finally, they had to be computationally tractable, meaning they could be solved within a reasonable amount of time, using standard computational resources.
It's a pretty tall order.
Yeah.
To come up with problems that meet all those.
It is, but they did.
Okay.
They really put together this amazing collection of problems.
Yeah.
That really are, truly unique and challenging.
That's amazing. So they have all these mathematicians coming up with these really tough problems. So they just kind of trust that they were all, perfect and error-free?
Well, no.
Or actually...
Was there some kind of review process?
Yeah, they had a very rigorous multi-stage review process to make sure that the problems were really high quality and error-free. Yeah. And this included blind peer review. So other expert mathematicians were scrutinizing each problem.
Interesting.
Looking for ambiguities, checking the solutions, assessing the difficulty level.
That makes sense. And what's fascinating is they actually found a surprisingly high error rate during this review process.
Oh, really?
Yeah, around 10%.
That's surprising for, something as precise as math.
It is.
You'd think
It's really.
that there would be very few errors.
It really highlights the importance of that rigorous review process.
Right.
Because, even in a field like math, human error can creep in.
Yeah.
So it's not just about catching those outright mistakes. It's also about refining the problems, making sure they're clear, unambiguous, as challenging as intended.
Right. So we've got these incredibly tough guess-proof problems.
Right.
But what kind of math are we actually talking about here?
Yeah.
Is it all super abstract theoretical stuff?
Frontier math actually covers a really broad range of mathematical domains.
Okay.
Number theory, combinatorics, algebraic geometry, those feature pretty prominently.
Okay.
But it also includes problems from areas like group theory, probability,
Wow.
even category theory.
So it's a real smorgasbord of mathematical delights.
It is. And this diversity really reflects
Yeah.
the expertise of all these mathematicians involved.
Right.
Right. And it ensures that the AI models are being tested
Okay.
on a really wide range of, mathematical knowledge and techniques.
Makes sense. Now, you mentioned that, it covers all these different fields of math.
Yeah.
How do they all, fit together?
Well, the paper actually includes this really cool visualization.
Okay.
It's a network diagram,
Okay.
and it shows how all these different mathematical subjects are interconnected within the problem.
Oh, interesting.
So you can actually see how, number theory, for example,
Yeah.
links to combinatorics and group theory
Yeah.
in some really fascinating ways.
So it's like a map of the mathematical landscape with these problems kind of weaving through
Yeah, kind of.
all these different areas,
Yeah.
connecting them in surprising ways.
Exactly. So we have a sense of the why behind frontier math, the types of problems it includes.
Right.
But how do the AI models actually approach these problems?
Yeah. How do they just stare at these equations and magically spit out answers?
Not quite. So the researchers developed something called an experiment-enabled evaluation framework.
Okay.
And this allows the AI models to write and execute Python code
Huh.
within a controlled environment
Okay.
to try different approaches to solving the problems.
So it's like giving them a virtual lab
Yeah.
where they can kind of experiment and play around with different ideas.
Exactly. And that's a lot like how a human mathematician would work.
Right. Right.
Tinkering with ideas on a whiteboard,
Mm-hmm.
trying different things, seeing what works.
Yeah. So it's not just about finding the answer.
Right.
It's about the process of exploration and refinement that leads to that solution.
And the framework even provides feedback
Okay.
to the models based on their code execution results.
Interesting.
So they can actually refine their approach based on what happens.
That's pretty neat.
And they run their code.
So it's like a real learning experience
Yeah.
in the AI.
It is.
So what were the results of this evaluation?
Well, even the most advanced models, like GPT-4,
Yeah.
really struggled. They solved less than 2% of the problems.
Less than 2%. Wow, that's a far cry from their performance on some of those easier benchmarks.
Yeah, it is.
It really shows the jump in difficulty that frontier math represents.
It really does.
And it's important to remember, it's not just about getting the right answer.
Right.
It's about understanding the reasoning, the logical steps, the creative leaps
Yeah,
that lead to that solution.
exactly.
I mean, even if a model, stumbles upon the correct answer,
Right.
it might not have gotten there through sound mathematical logic.
Yeah.
It could have just been a lucky guess,
It could have been.
which doesn't really demonstrate true understanding.
No. So frontier math is really designed to expose those weaknesses
Okay.
in reasoning, right?
Mm-hmm.
To separate that genuine mathematical insight
Right.
from mere pattern matching or lucky guesses.
So it's about getting to the heart of how they're thinking.
Exactly.
Not just whether they get the right answer.
Exactly.
And speaking of different approaches, did the researchers observe
Yeah.
any variations in how the models used this opportunity to experiment?
They did. So some models jumped to conclusions really quickly,
Okay.
submitting answers with very little experimentation,
Interesting.
while others were a lot more hesitant.
Okay.
They'd run multiple code blocks, explore different avenues
Yeah.
before committing to a solution.
That's fascinating. It's almost like the models have different personalities,
Yeah, it's really interesting.
different approaches to problem solving.
It is. It raises a lot of questions about, how they're trained, how they're internalizing these concepts,
Yeah.
and how those internal architectures actually influence their problem solving.
But, beyond just evaluating the AI models, The researchers actually went a step further, and they interviewed prominent mathematicians, including Fields medalists,
Wow.
to get their expert perspectives on frontier math.
That's really interesting. I mean, that's one of the things I really appreciate about this paper.
Yeah.
That they didn't just rely on the quantitative results.
Right.
You know,
Yeah.
from the AI evaluation, they actually went out and talked to the experts.
And got those human insights.
Exactly.
Yeah.
So what did these mathematicians have to say?
Well, they all agreed that the problems in frontier math were exceptionally challenging. Even for them. Even these experts with their decades of experience acknowledge that they themselves would need, considerable time and effort to solve many of these problems.
So it's not just the AI struggling here.
Right, exactly.
These are genuinely hard problems.
Yeah, and their insights went beyond just the difficulty level. They also shared their thoughts on the potential role of AI in mathematics.
Interesting.
And what's really interesting is they didn't see AI as a threat.
Okay.
But rather as a powerful tool that could actually augment human capabilities.
Okay.
They envisioned AI systems acting as assistants, helping with tedious calculations, verifying proofs, exploring potential solutions.
So freeing up, human mathematicians to focus on those more creative and conceptual aspects of their work.
So it's a vision of collaboration, not replacement.
That's great.
AI as a partner.
Yeah.
Enhancing human ingenuity, not supplanting it.
That's a much more hopeful vision, I think, than a lot of the sort of doomsday scenarios that we hear about.
Right, yeah.
So I like that.
Yeah.
Now, the paper also talks about how frontier math compares to other, benchmarks and tests.
Right, because there have been other attempts to, measure mathematical reasoning in AI.
Right.
So how does frontier math stack up against,
Yeah, so they talk about things like GSMAK, the AI Mathematical Olympiad, even some benchmarks that focus on, formal mathematics, where computer systems are actually used to verify mathematical proofs.
Yeah, so how does frontier math kind of fit into that landscape?
So frontier math stands out in a few key ways.
Okay.
First of all, it's just way more difficult.
Okay.
Most existing benchmarks focus on problems that a human could solve in seconds or minutes.
Yeah.
Frontier math problems are designed to take hours.
Wow.
Maybe even days.
So it's a different level of complexity.
It's a different level of complexity.
Okay.
Secondly, it's designed to be resistant to data contamination.
Right, because we talked about that earlier, how some of these other benchmarks use problems from publicly available data sets.
Exactly.
So there's a chance that the AI has already seen them during training, which gives them an unfair advantage.
Right.
It's like peeking at the answer key before the test.
Yeah.
Frontier math avoids that by using completely new unpublished problems.
Right.
So it's a true test of their reasoning ability.
It is.
Not just their memory.
Right.
Okay.
And what else? And third, it uses that automated verification.
Okay.
Which makes it really well suited for evaluating a wider range of models, including those that are, closed source, or where the internal workings are not fully transparent.
So you don't need a human to check the answers.
You don't.
Because the computer can do it.
The computer can do it.
Okay.
Objectively and automatically.
So that allows you to evaluate any model, regardless of, how it's built or what data it was trained on.
Right, exactly.
So it's a much more, comprehensive assessment of its capabilities.
So it's more challenging.
Okay.
More resistant to data contamination.
Yeah.
And more versatile in terms of evaluation.
So it's really a significant step forward
It is.
in evaluating these AI systems. And it's an ongoing project, right?
It is.
They're continuing to add new problems.
They're always adding problems.
Refining the difficulty ratings, and they're exploring new evaluation methods.
Absolutely.
So it's not just a static test.
No, it's dynamic, it's evolving, it's constantly kind of pushing the boundaries.
And I think that's really important.
It is.
Because AI is evolving so rapidly.
Right.
We need these benchmarks to keep up,
Yeah.
to really challenge these systems and see what they're capable of.
Absolutely. And, it's not just about, building AI systems that can solve complex math problems.
Right.
For their own sake.
It's about understanding intelligence itself.
Exactly.
Yeah.
It's about using these challenges to really understand the nature of intelligence.
Yeah, it's like holding a mirror up to ourselves.
It is.
Using AI to reflect back on our own cognitive abilities and to explore what's even possible in the realm of intelligence.
It is.
And I think that's what makes this research so fascinating, because it goes beyond just, the technical aspects of AI.
Right.
And it touches on these really fundamental questions about what it means to think, to reason, to be intelligent.
Exactly. It's a journey that we're really just beginning.
I agree.
And benchmarks like FrontierMath are going to be so important.
Absolutely.
In guiding that journey.
Because they give us a way to measure progress, to identify the challenges, and to inspire future research.
And to make sure that AI develops in a way that actually benefits humanity.
Exactly. It's about finding that balance between harnessing the power of AI and staying grounded in human values. Like creativity and ethical responsibility.
Absolutely.
So as we kind of, wrap up this part of our discussion of frontier math, what are some key takeaways that you hope our listeners will take away from this?
Well, first of all, I think it's just really important to recognize that there's still this big gap between the capabilities of AI and human mathematicians, especially when it comes to this kind of advanced mathematical reasoning. Right. Even the most sophisticated AI models are still struggling with problems that
humans can solve.
That experienced mathematicians can solve. And that just highlights how complex and nuanced human thought really is.
It does. It's a good reminder that intelligence isn't just about processing power or recognizing patterns. It's something much deeper than that. Secondly, I hope listeners will appreciate the importance of benchmarks like FrontierMath in driving AI research forward, because they provide that rigorous and objective measure of what AI can do. So it gives researchers a target to aim for, a way to identify where progress is being made.
It's a roadmap, right?
It is. It's a roadmap
for AI research
to guide us towards systems that can truly reason and solve complex problems.
Exactly.
And lastly, I think this research underscores the importance of approaching AI development with humility and responsibility. AI has the potential to revolutionize so many aspects of our lives. But it's crucial that we guide its development in a way that aligns with human values and aspirations.
It's about making sure that AI is a tool for human flourishing.
Exactly.
Not a replacement for human ingenuity or a threat to our economy.
Absolutely. And I think frontier math really forces us to grapple with these questions because it pushes the boundaries of AI in this very specific but important domain of mathematics. And it makes us think about the long-term consequences of AI's increasing influence on our world.
So it's a call to action in a way.
It is.
To have these conversations, to encourage responsible innovation, to work together, to make sure that AI's future benefits everyone.
It's a reminder that we're not just building machines. We're shaping the future of intelligence itself.
That's a great way to put it. And for those listeners who are feeling adventurous, I encourage you to check out the sample problems and solutions.
They're in the paper.
That the researchers have included in the paper.
It's a chance to test your own math skills. See how you stack up against the AI.
Maybe discover a hidden talent.
Exactly.
You never knew you had.
And even if you don't solve the problems, just wrestling with them, trying to understand the concepts.
It's a rewarding experience. You get a glimpse into the world of advanced mathematics.
It's a fascinating world.
It is.
Full of logic and creativity and just pure intellectual horsepower.
So keep those brains engaged, keep that curiosity burning.
Absolutely.
The world of knowledge is vast, and there's always something new to discover. So thanks for joining us on this deep dive into frontier math. Until next time, keep exploring.
Keep exploring. It really does, And it's important to remember it's not just about getting the right answer. It's about understanding the reasoning behind it, the logical steps, the creative leaps that go into finding that solution. Even if a model stumbles upon the right answer, it might not have gotten there through proper mathematical logic.
It might have just been lucky.
It could have just been a fluke. So frontier math is designed to really expose those weaknesses in the reasoning.
To separate the actual insight from just the lucky guess.
Exactly. And speaking of different approaches, did the researchers observe any variation in how the models use this opportunity to experiment?
They did. So some models were really quick to jump to conclusions, submitting answers with very little experimentation. And others were a lot more hesitant.
Interesting.
They'd run multiple code blocks and explore different avenues before actually committing to an answer.
That's fascinating. It's almost like the models have different personalities.
Yeah, it is interesting.
Different approaches to solving these problems.
Yeah. And it raises questions about how these models are trained, how they internalize these mathematical concepts, and how their internal architecture influences their problem-solving strategy.
Now, beyond just evaluating the AI models themselves, the researchers actually went a step further.
Okay.
And they interviewed some prominent mathematicians, including Fields medalists, to get their perspective on frontier math.
That's cool.
Yeah, and this is one of the things I really appreciate about this paper.
Yeah.
Is that they didn't just rely on the quantitative results from the AI evaluations. They actually went out and they talked to the experts.
They got the human insight.
They got that human insight.
Right.
Yeah. So what did these mathematicians have to say about frontier math?
Well, they pretty much all agreed that the problems in frontier math were exceptionally challenging.
Oh.
Even for them. Like these experts with decades of experience, acknowledged that they themselves would need a considerable amount of time and effort to solve many of these problems.
So it's not just the AI that's struggling.
No, it's not just the AI.
These are legitimately hard problems.
Yeah, these are really tough.
Yeah. And their insights went beyond just the difficulty level.
Okay.
They also talked about, what they thought the potential role of AI in mathematics could be.
Interesting.
And what was really interesting is that they didn't see AI as this threat to their profession, but rather as this really powerful tool that could really enhance what humans are capable of.
So like AI as an assistant, not as a replacement.
Exactly, yeah. Like helping with tedious calculations, verifying proofs, exploring potential solutions.
Freeing up the humans to do the more creative stuff.
Exactly, yeah. So it's this vision of collaboration, not replacement. AI is this partner that enhances human ingenuity, not replacing it. It's a much more hopeful vision than a lot of the doomsday scenarios we hear about.
I think so, yeah.
Right.
Now, the paper also talks about how frontier math compares to other benchmarks and tests that are out there.
Right, because there have been other attempts to measure mathematical reasoning in AI.
Right. They talk about things like GSMAK, the AI Mathematical Olympiad, and even some benchmarks that focus on formal mathematics, where computer systems are used to verify mathematical proofs.
Yeah, so how does frontier math fit into that?
So frontier math actually stands out in a few key ways. First of all, it's just considerably more difficult.
Okay.
Most of the existing benchmarks focus on problems that, a human expert
could solve in seconds or minutes.
Right.
Frontier math problems are designed to take hours, if not days.
Wow. So it's a whole other level.
It's a whole other level of complexity.
Right.
Second, it's specifically designed to be resistant to data contamination.
Okay, right. We talked about that earlier.
Right.
How some of these other benchmarks use problems from, publicly available data sets.
Exactly.
So there's always this chance that the AI has already seen them.
Right. It's like peeking at the answer key.
Exactly. It's like cheating.
Yeah.
So frontier math avoids that by using entirely new, unpublished problems.
Right.
So it's a true test of their reasoning ability, not their memory.
It is.
And third, it uses this automated verification, which makes it really well suited for evaluating a wider range of models, including those that are closed source, or where the internal workings aren't totally transparent, because you don't need a human to check the answers.
The computer can do it automatically.
Right, it's objective. And
objectively, yeah. So that allows you to evaluate any model, regardless of how it was built or what data it was trained on. So it gives you a more comprehensive assessment of its capabilities.
More challenging, more resistant to contamination, and more versatile.
Exactly.
So it's really a big step forward.
It is. It's a significant step forward in evaluating these AI systems.
It is, and it's an ongoing project.
It is.
So they're continually adding new problems.
Refining those difficulty ratings.
Refining the difficulty.
Exploring new evaluation methods.
Yeah, so it's not just this static test.
It's a living benchmark.
Yeah, it's dynamic, it's evolving,
yeah,
constantly kind of pushing the boundaries.
And I think that's really important because, AI is evolving so rapidly.
Yeah.
We need these benchmarks to keep up, to challenge these systems, to really see what they're capable of.
And it's not just about, building AI systems that can solve complex math problems just for the sake of it.
Right, exactly.
It's about using these challenges to understand intelligence itself.
It is. It's about understanding what makes us intelligent.
Yeah.
What makes these AI systems intelligent.
And how those things are similar or different.
Exactly. Yeah.
It's like we're holding a mirror up to ourselves.
It is.
Using AI to kind of reflect back on our own abilities.
And explore what's even possible.
That's possible.
In the realm of intelligence.
Yeah. It's a pretty amazing journey, really.
It's a fascinating journey, and it's one that we're just beginning.
We're just at the beginning.
Yeah.
And benchmarks like FrontierMath are going to be so crucial.
Absolutely, because they give us a way to measure our progress.
Right.
Identify the challenges, inspire future research.
And to make sure that AI develops in a way that benefits us.
Exactly.
Yeah.
It's about, harnessing this power,
Yeah.
but doing it in a way that is responsible.
Right. And aligned with human values.
Absolutely.
So, as we wrap up this part of our conversation about FrontierMath,
yeah,
what are some of the key takeaways that you hope our listeners will come away with?
I think, first of all, just recognizing that there's still this big gap between the capabilities of AI and human mathematicians.
Yeah.
Especially when it comes to this kind of advanced mathematical reasoning.
Right.
Even the most sophisticated AI models are still struggling with problems that
humans can solve.
Experienced mathematicians can solve. And that just highlights how complex and nuanced human thought is.
It really is. I mean, intelligence isn't just about processing power or recognizing patterns.
It's something much deeper.
It's something much, much deeper than that.
Secondly, I hope listeners appreciate how important benchmarks like FrontierMath are for pushing AI research forward, because they provide this rigorous and objective measure of what AI can do. It's a target to aim for, a way to measure progress.
It's like a roadmap for AI research, guiding us towards systems that can really reason and solve these complex problems.
Yeah. And lastly, I think this research shows us how important it is to approach AI development with humility and responsibility.
Yeah.
AI has incredible potential to revolutionize so many aspects of our lives.
It really does.
But it's crucial that we guide its development in a way that aligns with human values and aspirations.
So that AI is a tool for human flourishing.
Exactly.
And not a replacement for human ingenuity.
Yeah.
Or a threat to our autonomy.
Absolutely.
Yeah.
And FrontierMath, I think, really forces us to grapple with these questions.
Yeah, because it's pushing those boundaries in such a specific but important domain.
In this really important area of math that makes us think about the long-term consequences of AI's increasing influence in the world.
It's a call to action.
It is. It's a call to action.
To have these conversations.
To have these discussions.
To encourage responsible innovation. To work together. To make sure that AI's future benefits everyone.
It's a reminder that we're not just building machines.
Right.
We're shaping the future of intelligence itself.
That's a great way to put it.
And for those listeners who are feeling adventurous.
Yes.
I encourage you to check out those sample problems. And solutions that are included in the paper.
See how you do.
Yeah. See how you stack up against the AI.
Yeah. Maybe discover a hidden talent.
Yeah. Maybe you're a math whiz and you don't even know it.
Exactly.
And even if you don't solve the problems, just wrestling with them, trying to understand the concepts, it's a rewarding experience.
It is.
It gives you this glimpse into the world of advanced mathematics.
Right, where logic and creativity and just pure brain power collide.
It's a fascinating world.
It is.
So keep those brains engaged.
Yeah, keep that curiosity burning. The world of knowledge is vast, and there's always something new to learn.
That's right.
So thanks for joining us on this deep dive into FrontierMath. Until next time, keep exploring.
Keep exploring.
Yeah, it really makes you realize that we're not just building machines here. We're exploring the very nature of what it means to be intelligent.
It's true, yeah. I mean, FrontierMath, by challenging AI with these problems that require deep reasoning, creativity, this kind of almost like intangible spark of ingenuity.
Yeah.
It really helps us understand what intelligence even is.
Yeah, it kind of pushes those boundaries between human and artificial intelligence and makes us really question what it means to think and to reason.
Yeah.
And to solve problems in a world that's becoming increasingly complex.
Exactly. And I think the findings from this research, they have implications that go way beyond mathematics,
Right.
It touches on these fundamental questions about the nature of thought.
Yeah.
The limits of what computers can do. What the future of intelligence might look like in a world where AI is playing a bigger and bigger role.
And we're just at the beginning of this journey.
It's scratching the surface.
And benchmarks like FrontierMath are going to be so essential in guiding us.
Oh, absolutely, because they provide this framework, this structure for evaluating progress, for identifying the challenges, for inspiring new research.
And to make sure that we're developing AI in a way that actually benefits humanity. Right?
Exactly, yeah. It's about, harnessing the incredible power of AI, but doing so in a way that is responsible, that aligns with human values.
Right. So as we kind of wrap up our deep dive into FrontierMath here, what are some of the key takeaways that you hope our listeners will kind of carry with them?
I think first and foremost, it's crucial to recognize that there's still a very significant gap between the capabilities of current AI systems and human mathematicians, especially when it comes to this advanced mathematical reasoning.
Yeah.
I mean, even the most sophisticated AI models today are still struggling with problems that, experienced mathematicians can solve.
Yeah.
And that really highlights the incredible complexity and the nuance of human thought.
It's a good reminder that intelligence isn't just about processing power or recognizing patterns.
Yeah.
It's something much deeper.
It's something much, much deeper than that. Secondly, I hope listeners will appreciate the critical role that benchmarks like FrontierMath play in pushing this research forward, because they provide this rigorous and objective and incredibly challenging measure of what AI can actually do.
Yeah, it's a target to aim for.
It is. It's a target. It helps researchers identify areas where progress is being made and where more work needs to be done.
It's a roadmap for AI research in a way, right?
It is. It's a roadmap guiding us towards systems that can truly reason, that can solve complex problems.
And can contribute to our knowledge.
Exactly.
Yeah.
And lastly, I think this research really underscores how important it is to approach AI development with a sense of humility and responsibility. I mean, AI has the potential to revolutionize countless aspects of our lives.
Oh, absolutely.
But it's crucial that we guide its development in a way that aligns with human values and aspirations.
Yeah. It's about making sure that AI serves as a tool for human flourishing.
Exactly.
And not as a replacement for human ingenuity or a potential threat to our autonomy.
Precisely. And FrontierMath, by kind of pushing those boundaries of AI in this very specific but profoundly important domain of mathematics, it really forces us to grapple with these fundamental questions and to consider the long-term consequences of AI's increasing influence on our world.
Yeah, it's a call to action in a way.
It is a call to action, urging us to have these conversations, to encourage responsible innovation.
To work together.
To work together, to ensure that AI's future unfolds in a way that benefits all of humanity.
It's really powerful. And for those listeners who are feeling adventurous, I encourage you to check out the sample problems and their solutions.
Oh, yeah.
That the researchers included in the paper.
It's a great way to kind of test your own math skills.
Yeah.
See how you stack up against these AI systems.
Yeah, maybe discover a hidden talent you never knew you had.
Exactly. Yeah. And even if you don't manage to solve the problems, just wrestling with them.
Right.
Trying to wrap your head around the concepts involved.
Yeah.
It's a really rewarding experience in itself.
It is.
It's a glimpse into this world of advanced mathematics.
Right, where logic and creativity and just pure intellectual horsepower collide.
Exactly.
So keep those brains engaged. Keep that fire of curiosity burning. The world of knowledge is vast, and there's always something new to discover, something new to challenge ourselves with.
That's right.
Thanks for joining us today on this deep dive into the world of FrontierMath. Until next time, keep exploring.
Keep exploring.
Hey there. Ready for some seriously challenging math?
I think we're both ready for this one.
Yeah, I've been looking forward to this deep dive all week. Today, we're going to explore this brand new benchmark called FrontierMath.
Sounds intimidating already.
And trust me, it's not your average high school algebra. Think of it as the Mount Everest of AI math tests.
Mount Everest.
Yeah. We're talking problems that make even, seasoned mathematicians scratch their heads for hours, even days.
That's right. FrontierMath is designed to push the boundaries of what AI can achieve in mathematics. We're moving beyond basic arithmetic and stepping into the realm of cutting-edge research.
So we're talking about, abstract algebra?
Abstract algebra, for sure.
Complex number theory.
Yep, complex number theory, too. All that good stuff.
And the coolest part.
What's that?
All the problems are brand new, never before seen.
Oh, that's interesting. So no chance of AI models cheating by recognizing them from training data?
Exactly. It's a true test of their reasoning and problem-solving abilities, pushing them to think like real mathematicians.
So let's get into it. What exactly is FrontierMath?
Well, it's a benchmark, right? But it's designed to address a couple of really big limitations that have been plaguing existing benchmarks.
Okay, I'm intrigued. What limitations are we talking about here?
Saturation and data contamination.
Okay. Let's break those down a bit. Starting with saturation, what does that even mean in this, AI and mathematics kind of world?
Well, think of it like this. You've got these AI models, right? They get so good at these existing benchmarks that they basically ace them.
Like a student who's just memorized all the practice tests?
Yeah, exactly.
Yeah.
And it leaves very little room for actually measuring, how much they're actually learning and progressing.
So they need a next level challenge, something that forces them to really think and not just regurgitate what they've seen before.
That's exactly what FrontierMath aims to do.
Okay, I'm with you on saturation. But what about this data contamination thing? How does that mess up these AI evaluations?
So imagine this. The AI models have actually been trained on data that includes the actual test questions.
Whoa.
Or at least questions that are very similar. Talk about an unfair advantage.
That's like giving them the answers beforehand. It completely defeats the purpose of a test.
It's not a true measure of their understanding at all.
So how does FrontierMath deal with this?
All the problems, every single one, they're completely original. Never seen before by these AI models.
Oh, I see. So it's a genuine test of their ability to problem solve. They have to think on their feet, right? Like a real mathematician facing an unknown problem.
Right. No pre-programmed solutions, no shortcuts.
Okay, that's pretty impressive. But how do they guarantee that these problems are actually good quality? I mean, in terms of both mathematical rigor and relevance to actual research.
Well, the problem creation process itself is super rigorous. They had over 60 expert mathematicians from, leading institutions all over the world involved.
Wow, that's a lot of brain power. So it's a real collaborative effort, huh? By some of the, brightest minds in math.
Definitely. And they created these problems to meet some very specific criteria.
Okay, let's hear it. What are these criteria that make a FrontierMath problem?
There are 4 of them, and they're really important.
At me.
First, originality.
Makes sense, considering what we just talked about.
Second, automated verifiability.
Okay.
Third, guess-proofness.
Interesting.
And finally, computational tractability.
All right, let's break those down one by one. Originality, I'm assuming, means the problems are brand spanking new.
You got it. Never published before. This stops the AI models from just pulling out solutions from their training data. They got to think critically.
Okay, originality check. What about automated verifiability? Why is that so crucial?
Well, it guarantees that the AI's solutions can be checked by a computer program.
So no room for human bias in the evaluation.
Exactly. And it allows for super quick and consistent scoring.
Like an instant judge, right?
Yep. Now, guess-proofness, this one's really clever.
How do they make sure the AI can't just, get lucky and stumble on the right answer?
The problems are designed in a way that makes guessing the answer super unlikely.
Ah, so the AI actually has to reason its way to the solution.
Right. It's not just about finding the answer. It's about understanding how to get there.
Gotcha. All right, last but not least, what's this computational tractability all about?
It means that the solutions, even though they're complex, can be computed in a reasonable time.
Reasonable time meaning?
Typically under a minute.
Okay, so it's got to be practical, something that can be done with the computing resources we have.
Right. Not some calculation that would take like a supercomputer years to solve.
Right, right. So it's about finding solutions that are both correct and efficient.
Exactly. Makes sense, right?
Absolutely. It reflects the real-world constraints of doing math, even for us humans. Okay, so we've got these super tough problems designed with these 4 criteria in mind. But how does this automated verification actually work? What kind of answers are these AI models spitting out?
They usually have to give their answers in a format that a computer program can easily check, like numbers, symbolic expressions, or even code that generates the answer.
So it's not enough to just write down an answer. They have to produce something verifiable.
Exactly. And that makes the whole evaluation process faster, more objective, and less prone to, human errors.
Okay, I'm following you. But if we're only focusing on these automatically verifiable answers, doesn't that kind of limit what FrontierMath can test? I mean, math is so much more than just churning out numbers, right?
You're right. Like, proofwriting is a huge part of math, and right now, FrontierMath doesn't include those tasks.
Why not? Seems like a pretty important piece to leave out.
It all comes down to evaluation. Evaluating proofs would need humans, which would make things subjective and slow down the whole process.
So it's a trade-off. They gain efficiency and objectivity by sticking to verifiable answers, but they lose the ability to test the AI's, logical reasoning and proof construction skills.
For now, at least.
Right, right. But even without proofs, these problems are still crazy hard, right?
Oh, yeah. They require a deep understanding of these, advanced math concepts. And the AI has to apply them in new and creative ways.
Okay, I'm convinced they're tough. But how can we be sure that the problems themselves are actually good, free of errors, ambiguities, that kind of thing? Math can be pretty subtle, and even a small mistake can lead to a completely different solution.
That's true. That's why every single problem goes through a multi-stage review process, and it all starts with a blind peer review.
Blind peer review, meaning other mathematicians check it out without knowing who wrote it.
Exactly. That helps eliminate bias and ensures the review is based on the problem itself, not the person who came up with it.
Makes sense. And these reviewers are experts in those specific areas of math, right?
Oh, yeah. They scrutinize everything. The statement, the solution, the wording, making sure it's guess-proof, even the difficulty rating.
Wow, so it's like a super thorough quality control system.
Definitely. And on top of that, they have a second review process. It's like a random spot check of the problems to figure out a reasonable error rate.
So they are finding some errors. What kind of error rate are we talking about here?
It's about 10%.
10%? Is that a lot?
It's not insignificant, but it's actually within the normal range for, machine learning benchmarks, especially when you're dealing with something as complex as advanced math.
I guess that makes sense. So what kind of stuff are they finding?
Some minor things, like missing parts in some problem statements or places where guessing might be a little easier than they planned. But overall, the quality is very high.
Okay, that's reassuring.
Yeah.
So what kind of math does FrontierMath actually cover? Is it all just one specific area, or is it more diverse?
It's pretty diverse. It covers most of the top-level subjects in this thing called the MSc 2020 classification.
MSc 2020.
Yeah, it stands for Mathematics Subject Classification. Basically, it's a system for classifying all the different areas of math.
Like a Dewey Decimal System for math.
Right. And FrontierMath casts a pretty wide net.
So what kind of areas are we talking about?
Everything from foundational stuff like number theory, combinatorics, to more specialized areas like algebraic geometry, topology, and even category theory.
Wow, it really runs the gamut.
But it's not just a random collection of problems from all these different areas.
What do you mean?
A lot of the problems actually combine elements from multiple fields.
Oh, interesting. So the AI has to integrate knowledge from different areas.
Yeah, it's like solving a puzzle, but the pieces come from different boxes.
That sounds really tough. Can you give me an example of how they do that?
Well, about 13% of the problems combine number theory and combinatorics. And those core fields, like number theory, combinatorics, and group theory, pop up in a good chunk of the benchmark.
I see. It reflects how real-world research often happens at the intersection of different fields.
Exactly. And that interconnectedness makes frontier math even more challenging and more relevant to actual mathematical research.
Okay, this is all fascinating, but let's step back for a second. How does all this, this whole evaluation setup in frontier math compared to how human mathematicians actually work?
It's actually designed to be pretty similar. It's what they call experiment-enabled.
Experiment-enabled, what's that?
It means that the AI models aren't just given a problem and expected to spit out an answer. They can actually write code, run experiments, see the results, and then, like, adjust their approach based on what they learn.
So it's like giving them their own little math lab, right?
Yeah, where they can test things out, explore, make mistakes, just like a human mathematician would.
It sounds a lot more realistic than just, feeding them a problem and expecting an instant answer.
It is. So when they're ready to submit their final answer,
okay, how does that work?
they got to follow a specific protocol.
Yeah.
They put a special comment in their code to signal the final answer.
Makes sense. Got to be clear about what they're actually submitting.
And then they pickle their answer.
Pickle.
It's a Python thing. It's basically a way to save their answer in a standardized format so it can be easily checked.
Ah, so everything's neat and tidy for the computer to verify.
Exactly. Oh, and they also have a token limit.
Tokens again. Remind me what those are.
They're like the building blocks of the language model. Think of them as pieces of words, symbols, code. The token limit basically restricts how much thinking the AI can do.
So it's not just about getting the right answer. It's about getting there efficiently.
Yep. Which adds another layer of difficulty.
It does. It's like a real-world constraint. You often don't have unlimited time and resources to solve a problem.
Exactly. Okay, I'm really curious now. How have these AI models been doing on FrontierMath? Have they managed to crack these crazy hard problems?
Well, the results have been pretty humbling, to be honest. Even the most advanced models, like GPT-4o, Claude 3.5 Sonnet, Gemini 1.5 Pro, they're all under a 2% success rate.
Wow. That's a huge difference from how they perform on those easier benchmarks.
Right. It really shows the gap between where AI is now and, the level of mathematical thinking needed to handle frontier math.
It's clear that advanced math reasoning is much more than just pattern recognition or symbol manipulation. You need a real understanding of the concepts and the ability to apply them in creative ways.
Absolutely. And frontier math is really pushing the boundaries of what AI can do in this area.
So before we move on to look at some examples, I'm curious about one more thing.
Sure. What is it?
You mentioned that the AI models can use code in their answers. Does that mean they can actually write mathematical proofs?
Ah, that's a great question. The current version of frontier math doesn't have proofwriting tasks, mostly because it's really hard to evaluate those automatically. But, the fact that AI can generate code opens up some really interesting possibilities.
Like what?
Well, imagine an AI that not only solves a problem, but also writes code that, represents the logic of its solution.
So it's basically creating a formal proof that a computer can verify.
Exactly. That would be a huge leap forward, wouldn't it? It would show that the AI isn't just finding an answer, but it actually understands the reasoning behind it.
It's definitely something to think about. It would be amazing to see how AI tackles the challenge of proofwriting.
It would. And it highlights how frontier math is constantly evolving, pushing those boundaries.
Well, this has been an amazing overview. I'm really starting to grasp what frontier math is all about.
Me too. It's clearly a game changer in the world of AI and mathematics.
So, ready to dive into some actual problems. I'm dying to see what these things look like.
Absolutely. Let's see what kind of mathematical beasts frontier math has cooked up. All right, so are you ready to see some of these frontier math problems?
I'm definitely curious, yeah. But honestly, after hearing how much those AI models are struggling, I'm also a little intimidated.
I get it. They are designed to be really challenging. Want to start with one of the hardest ones?
Sure. Lay it on me.
Okay, this one is from the paper, and it's classified as a research-level number theory problem. It's called Testing Artin's Primitive Root Conjecture.
Okay, the name alone sounds intense. What even is Artin's primitive root conjecture?
So it's a famous unsolved problem in number theory, and it basically asks us a really simple-sounding question.
Okay, I'm listening.
For a given integer, are there infinitely many prime numbers where that integer is a primitive root?
Primitive root. Can you remind me what that is again?
Right, of course. So a primitive root of a prime number, we'll call it p, is an integer, a, that when you raise it to different powers modulo p, it can generate all the numbers from 1 to p1.
So it's like that special number that can create all the other numbers within that prime numbers world.
Exactly. And Artin's conjecture wants to know if, for any given number, you can find infinitely many prime numbers where that number acts as this, like generator.
That's a pretty deep question. So does this frontier math problem actually ask the AI to prove or disprove this conjecture?
Not exactly. That would be a huge task, even for the best human mathematicians. Instead, the problem focuses on a specific calculation that's related to Artin's conjecture. It has to do with the order of the numbers 2 and 3 modulo a prime p.
Okay, hold on. Break that down for me. What does order even mean in this context?
So the order of an integer a modulo p is the smallest positive integer k, where a raised to the power k is congruent to 1 modulo p. It basically tells you how many times you have to multiply a by itself until you get back to 1 in this like modulo p world.
So it's like a loop where you keep multiplying and multiplying until you circle back to the beginning.
Yep, that's a good way to think about it. And this frontier math problem is all about looking at the relationship between the orders of 2 and 3 for a bunch of different prime numbers. It wants you to figure out a specific density related to how often the order of 2 is greater than the order of 3.
I see. So it's not directly proving or disproving Artin's conjecture, but it's exploring a specific mathematical property that's connected to it. Sounds pretty complicated. What kind of math do you even need to use to solve this?
It's deep into algebraic number theory territory. You would need tools like the Chebotarev density theorem, which helps you understand how prime numbers with certain properties are distributed. It even touches on a generalized version of the Riemann hypothesis.
Wait, the Riemann hypothesis? Like one of the biggest unsolved problems in all of math.
The one and only.
Okay, this is getting seriously intense. I can definitely see why AI is having a hard time with these.
It really shows how challenging these problems are.
All right, let's move on to another one. What else do you have?
Okay, how about a problem from algebraic geometry and group theory? In this one, you have to construct a specific polynomial of degree 19.
Polynomials, like those things we used to graph back in algebra class.
Yeah, but this is a much more specialized kind of polynomial. It has to be odd, meaning only odd powers of x show up, and it has to be monic, meaning the coefficient of that highest power of x is 1. It also needs to have real coefficients, and the coefficient of the x term has to be 9 to 19.
Okay, that's really specific. But what makes it so difficult? I mean, it's just a polynomial, right?
Well, the real challenge comes from thinking about this polynomial geometrically. When you plot the points where this polynomial equals itself, you get a curve. And this curve has to have some very specific properties.
Like what?
It needs to have at least 3 irreducible components, but not all of them can be linear.
Hold on. Irreducible components. Can you explain that in like normal human language?
Sure. Imagine you have this complicated shape, right? And it's made up of a bunch of simpler curves all joined together. An irreducible component is like the most basic building block of that shape. It's a piece that you can't break down into any simpler curves.
So it's like a prime number, but for curves.
Exactly. You can't factor it any further. And this problem is asking you to find a polynomial that creates a curve with this very particular structure.
Okay, I'm starting to see how this mixes algebra and geometry in a really tricky way. What kind of math concepts do you need to solve this one?
You're getting into some pretty advanced stuff here. Things like monodromy, which is about studying how solutions to equations change when you move around singularity, and branch loci, which are points where those solutions start to like branch out or behave differently. And you even need to know about the Riemann existence theorem.
The Riemann what now?
The Riemann existence theorem. It's this really powerful tool that connects complex analysis and algebraic geometry.
Okay, you're definitely speaking a different language now.
I know, it's a lot, but it really highlights the multidisciplinary nature of these problems.
Yeah, it's definitely a challenge. Okay, maybe we can look at something a little different now.
Sure, let's switch gears. How about a graduate level number theory problem? This one gives you a sequence of integers, and they're defined by this pretty complicated recurrence relation.
Recurrence relation meaning like each number in the sequence depends on the ones before it.
Exactly. It's like a recipe that tells you how to get the next number based on the previous ones. And the challenge here is to find the smallest prime number that fits certain conditions related to this sequence.
Okay, what kind of conditions are we talking about?
We're getting into p-adic number territory here.
Uh-oh.
Yeah, it's pretty advanced stuff. Basically, you need to find a prime number p that allows a specific function which maps an integer n to the nth term of this sequence to be extended to a continuous function on the, get this, p-adic integers.
P-adic integers. Okay, I think you've officially lost me. Is there any way to explain that without needing a PhD?
Okay, let's try this. Imagine you have this magnifying glass.
Yeah.
Right? And it lets you zoom in on numbers in a different way than usual. Instead of looking at the decimal expansion, you're looking at how divisible the number is by powers of a specific prime number, p.
Okay, I'm kind of following.
So the p-adic integers, they're like this whole world where numbers are considered close if they're both divisible by really high powers of p. It's a different way of measuring distance between numbers.
So it's like a whole new perspective on numbers based on their relationship to a specific prime.
Yes. It's a bit mind-bending, but it's incredibly useful in number theory. And this problem is all about finding a prime number that makes the sequence behave nicely in this weird, p-adic world.
All right, I think I get the gist of it. It's not just about the sequence itself, but how it connects to this deeper, more abstract concept.
Exactly. And that's what makes these problems so challenging. They bridge different areas of math.
What kind of math tools would you need to actually solve this one?
Well, you'd need to understand things like the Skolem-Mahler-Leck theorem, which is all about how linear recurrent sequences work. Then you'd need to know p-adic analysis, which is kind of like calculus, but in this p-adic world. And you even need to know how familiar functions, like exponentials and logarithms, behave in this setting.
Sounds like a whole semester's worth of advanced math packed into one problem.
It's definitely not for the faint of heart.
Okay, my brain needs a break from all this number theory. Can we switch to something a little different, maybe?
Of course. Let's look at a problem that combines linear algebra and group theory. This one's actually labeled as medium-low difficulty, so it should be a bit easier to grasp, relatively speaking.
Matrices and groups. Okay. I feel a bit more comfortable with those. What's this problem all about?
It involves a set of 4 tuples, and each element in the tuple is an invertible 1000 by 1000 matrix.
Invertible, meaning it has an inverse. Like you can multiply it by another matrix and get back the identity matrix.
Exactly. And these matrices have to satisfy certain conditions involving commutation relations and braid relations.
Commutation relations. That means the order you multiply some pairs of matrices in doesn't matter, right? And braid relations.
Braid relations are a little more complicated. There's specific ways you can rearrange the order of multiplication for 3 or more elements. It's kind of inspired by how strands in a braid can be woven together.
Interesting. Okay. So we've got these 4 tuples of matrices with all these special rules for how you can multiply them. What's the problem actually asking for?
It wants you to figure out the number of orbits of a specific group action on this set of 4 tuples.
Group action. Okay, that sounds abstract.
Think of it like this. You've got a group of transformations, like rotations or reflections, and you apply them to a bunch of objects. The group action describes how that group acts on or changes those objects. In this case, the group is the general linear group, GL1000, which is all the invertible 1000 by 1000 matrices.
Okay, so we're seeing how these invertible matrices can change our set of 4 tuples.
Right, and each orbit represents a bunch of 4 tuples that can be transformed into each other by these group elements.
So it's like grouping together all the 4 tuples that are basically the same, just rearranged or transformed in different ways.
You got it. And to solve this problem, you need to dive into the representation theory of the symmetric group S5.
Symmetric group? What's that?
It's the group of all the ways you can permute or rearrange 5 objects. It turns out to be really important for understanding the structure of matrices and how they can be transformed. To solve this problem, you need to know about things like Coxeter relations, which are like the basic rules for the group, and character tables, which are a tool for studying how groups are represented.
Okay, this one's definitely easier to follow than those number theory ones, but it's still pretty complex. Lots of linear algebra, group theory, and seeing how they connect.
It is. It's a great example of how FrontierMath combines different areas of math in these really interesting and challenging ways.
Okay, ready for one last problem?
Sure. This one's labeled as low difficulty, and it's all about counting the number of points on a particular curve over a finite field.
Finite field? That's like a set of numbers with only a finite number of elements, right?
Yeah.
With its own rules for arithmetic.
Exactly. In this case, the finite field is F518, which has, as you might guess, 518 elements. It's like a self-contained mathematical universe.
518 elements. That's a lot to keep track of.
It is. And the curve in this problem is defined by this equation. By 3y plus y3z plus z3x equals 0.
Okay, so we have all the points in this finite field that satisfy that equation.
You got it. But there's a catch. You're counting the points up to scaling.
Up to scaling.
It means that if you have a solution, like x, y, z, and you multiply all 3 coordinates by the same non-zero number from the field, it's considered the same solution.
So we're only looking for fundamentally different solutions, not just scaled versions of each other.
Right. And to count those, you need to use something called the Haswell bound. It's this powerful tool from algebraic geometry that tells you about the number of points on a curve based on the genus of the curve and the size of the field. Yeah, the genus of a curve is like a measure of its complexity. You can think of it as the number of holes in the curve. Like a circle has genus 0, a donut has genus 1, and so on.
Okay, that makes sense.
So to solve this, we need to figure out the genus of this particular curve and then use this Hasse-Weil thing to estimate the number of points.
Exactly. But you also need to check that the curve is smooth at a specific prime. This is important for applying the Hasse-Weil bound correctly.
Smooth meaning it doesn't have any, like, sharp corners or kinks.
Right. Mathematically, it means the curve has a well-defined tangent line at every point.
So even the easiest frontier math problem uses some pretty high-level math.
It does. It just goes to show that even these seemingly simpler problems can touch on some pretty deep mathematical concepts.
Well, we've looked at 5 problems now, and each one has been a different kind of challenge. I have to admit, even the easiest one left me feeling a little overwhelmed.
I understand. But that's the point of frontier math, right? It's pushing the boundaries of what AI can do in math. And it's a reminder of just how vast and complex the world of mathematics really is.
It's exciting, though, to think about the potential of AI to tackle these kinds of problems.
It is. And remember, the goal isn't to have AI replace human mathematicians. It's about developing systems that can work alongside us as powerful tools to help us explore and understand the universe of mathematics even better.
That's a great point. It's not about AI versus humans. It's about AI and humans working together.
Exactly. And speaking of human mathematicians, the paper we're looking at also includes some interviews with some really prominent figures in the field. They all weighed in on frontier math.
Oh, I'd love to hear what they had to say.
Yeah.
So who did they talk to? Which math superstars?
Oh, they got some big names like 3 Fields medalists, Terence Tao,
Wow.
Timothy Gowers, and Richard Borchards.
Amazing.
And they also interviewed Evan Chen. He's a well-known math educator. He coaches for the International Math Olympiad.
Okay, so what did they think about frontier math? Did they think it was a good test of advanced math?
They were all pretty impressed, especially with those research-level problems. They said even experienced mathematicians would find them tough.
So even without those formal proofs, it's still a big challenge for AI.
Definitely.
What about the AI's performance so far? Did they think AI was going to, like, overtake humans in math anytime soon?
Most of them were pretty skeptical about that. They acknowledged that AI has come a long way, but they said that real mathematical expertise needs more than just, number crunching or pattern recognition.
Right. There's that intuition, that creativity that's hard to program.
Exactly.
Did they think AI would ever get there? To that level?
They didn't rule it out completely, but they were hesitant to give any, specific timelines.
Yeah, that makes sense.
Terence Tao, for example, he thought it could take several years, at least, for AI to really understand math deeply enough to rival humans.
That's a long time.
It is, yeah. But Evan Chen thought that collaboration between AI and humans could speed things up.
So it's not really AI versus humans. It's more like AI with humans.
Yeah, exactly. And they talked about some pretty cool ways that AI could be used in math, even if it doesn't completely replace us.
Like what? What could AI actually do to help mathematicians?
Well, Timothy Gowers thought AI could be really good at handling those tedious parts of research, like verifying conjectures, doing complicated calculations, finding patterns in big data sets, stuff like that.
So it frees up the mathematicians to focus on the creative thinking and the big picture stuff.
Exactly. And Terence Tao thought AI could be used to tackle those really difficult problems that would take humans forever to solve. But he said it would have to be really computationally efficient to be useful.
Right. If it takes the AI longer to solve a problem than it takes a human, what's the point?
Exactly. Overall, I think they were cautiously optimistic about AI in math. They see it as a powerful tool that can help us, but not necessarily replace us.
That's really interesting. Frontier math is definitely at the forefront of all this, isn't it?
It is, yeah. And it's making people think hard about the future of math and AI and how they can work together.
Well, this has been an incredible deep dive. We've covered so much about frontier math.
I know, it's been a lot.
Its goals, how the problems are created, the evaluation process, the results so far, and even what these amazing mathematicians think about it all.
And we even talked about some of its limitations, like how it doesn't include proofreading yet. And those time constraints don't really reflect how math research often works in the real world.
Right. It's still work in progress, but it's already pushing the boundaries and getting people excited about what's possible.
Absolutely.
Who knows, maybe one day we'll have AI that can not only solve these frontier math problems, but actually work with us to discover new math,
That would be amazing.
It would. Thanks for joining us for this deep dive into frontier math. We hope you learned a lot, and until next time, keep exploring.